Welcome back to the deep dive. Today, we are really rolling up our sleeves. We're taking a significant step into the, let's say, rigorous, sometimes intimidating mathematics that's really driving the next generation of AI.
That's right. We're tackling one of the, frankly, toughest challenges out there in optimization theory right now. Constrained, non-convex, non-concave minimax problems.
It sounds like a mouthful, and it is, but this isn't just theory for theory's sake.
Not at all. If you, the listener, are working with things like generative adversarial networks, GANs, or trying to build really robust machine learning models, maybe doing sophisticated adversarial training, you are bumping up against this exact problem structure, whether you realize it or not.
And the difficulty, where does it really come from?
Well, fundamentally, you've got these two opposing forces, right? A minimizer, maybe trying to generate a fake image, and a maximizer, the discriminator, trying to catch it. Or maybe it's robustness, where one player tries to minimize loss while the other maximizes some perturbation.
Okay, a game between two players.
Exactly. But the killer is that neither player has a nice, smooth landscape to navigate. The minimizer's objective might be non-convex, full of hills and valleys, and the maximizer's objective might be non-concave, which is the equivalent problem for maximization. It's messy.
And on top of that messiness, this paper we're diving into today, a first-order method for constrained, non-convex, non-concave minimax problems under a local Kurdyka-Ło condition by Liu and Wang, it adds another layer, doesn't it? It zeroes in on the constraints.
Precisely. That's the real contribution here, tackling the constraints, specifically on the maximizer. A lot of prior work handled the unconstrained case, or maybe simple constraints, but complex constraints on that inner maximization player, that's been a major bottleneck.
So what's our mission for this deep dive? What should you, our listener, expect to get out of this?
Our mission, and it's ambitious, is to really truly grasp the analytical foundation that Liu and Wang built here. We need to understand their novel approach, focusing intensely on the core geometric assumption they make this thing called the local Kurdyka-Ło condition, or KL condition for short.
KL condition. Okay, we'll need to unpack that thoroughly.
Absolutely. And we need to understand the two algorithms that spring from this assumption. We're going to unpack the rigor, like literally notation by notation, definition by definition. We want to see exactly how they manage to get provable complexity guarantees, meaning how fast the algorithm converges in this landscape, where previously we often just had heuristics or methods that worked only under much stronger assumptions.
All right, let's start at the beginning then. The problem itself. The paper defines the primary form right up front. They call it problem 1. Can you lay that out for us?
Sure. It looks like this mathematically. Dominx px plus px qy.
Okay, that is dense. Lots packed in there. Let's dedicate some serious time just breaking down the rigorous terminology. Every single symbol here matters. It defines the nature of the beast we're wrestling with.
Agreed. Let's take it piece by piece. First, the function 5xry. This is sort of the core interaction term between the minimizing player $6 and the maximizing player 6. It's assumed to be smooth, meaning it has continuous gradients.
Smooth sounds nice.
It is, relatively speaking, but here's the catch. Its structure is what causes the headaches. It's potentially non-convex in the minimizing variable $6. So for a fixed YAL, the function might have multiple local minima for $6.
Okay, that's the minimizer's problem.
And simultaneously, it's potentially non-concave in the maximizing variable, the DAL. For fixed $6, the function might have multiple local maxima, or plateaus, for YAL. This lack of convexity in $6 and lack of concavity in YAL, that's the signature challenge of these general minimax problems.
Got it. Non-convex, non-concave. That's the core difficulty. What about the other terms, PXI and PYL?
These are, thankfully, a bit simpler. They are assumed to be simple, closed, and convex functions. The term simple usually means their proximal operators are easy to compute.
Proximal operator, like a generalization of projection.
Exactly. Think of PXI and Y as handling things like L1 regularization for sparsity, or maybe box constraints, simple constraints on the domains of $6. They add structure, but it's a manageable convex structure. They're the predictable parts of the problem.
Okay, so $5 is the complicated interaction. PCL or dollar are simple, convex regularizers. But you said the real kicker, the part that makes this paper necessary, is the constraint.
Precisely. Look at the maximization part. The variable dollar isn't just being maximized over its entire domain, it's restricted. Psi y is a smooth mapping, potentially vector valued, representing a set of constraints. Psi of y means it has to live within some feasible region defined by these potentially complicated nonlinear constraints.
And why is that so much harder than, say, just having a simple box?
Because the inner maximization problem is already non-concave due to $5. When you add complex constraints on top of that non-concave objective, the feasible regions for hay can become very tricky. Finding the maximum, even approximately, becomes a really hard optimization problem in its own right. Before you even think about the outer minimization over $6, standard methods just break down.
So this specific structure, problem 1, with the constrained inner maximization, isn't just some arbitrary setup. It has real-world relevance.
Oh, absolutely. It's not just a convenient simplification. It arises directly as a critical subproblem when you try to tackle the even more general constrained minimax problem, which the paper calls Problem 2.
Problem 2, what does that look like?
Problem 2 adds constraints to the outer player as well. So now you have constraints to the minimizer, 6 wire topples, in addition to the constraints on the maximizer.
Okay, that looks even more complicated. How does solving problem 1 help with problem 2?
We use a pretty standard technique from optimization, the penalty method. You take those outer constraints, checker dollar, and you sort of fold them into the objective function using a penalty term. You create a sequence of problems indexed by color.
How does that look?
For each color, you solve. Here, drunk X plus PX plus PX means you only penalize violations, where drunkest is positive, and drunkest is a penalty parameter.
And what happens with the rape?
You let genelec go to infinity as denal increases. Intuitively, you're making the penalty for violating the delay constraints increasingly severe. As devoted to infinity, the solutions to the sequence of penalized problems should, under reasonable conditions, converge to the solution of the original fully constrained problem 2.
Ah, I see it now. If you look at that penalized problem for a fixed, large del I low plus mix lilax plus P plus dental X up plus 2AY, that looks exactly like the structure of problem 1.
Exactly. The penalized function, the Delian core, is still smooth, if Diller is smooth, potentially non-convex and $6 non-concave. And so solving the general problem 2 often involves repeatedly solving subproblems that have the exact form of problem 1. Mastering the math for problem 1 is therefore essential. It's the workhorse subproblem.
Okay, that context is crucial. So understanding problem 1 unlocks the door to the more general case. Let's move into the formalization then. Section 1, formalizing the mathematical landscape.
Right. And the authors are very clear here. The tools that might work for simpler, unconstrained minimax problems, maybe like the one they label problem 3, which is just max EF subtract, those tools, like basic gradient descentescent, are just not enough for problem 1.
Why not? What breaks?
Well, two main things. First, the non-smoothness introduced by the max operator and potentially the functions 2 on dollars. Standard gradients don't exist everywhere. Second, and crucially, the constraint leather. Handling that requires more sophisticated machinery.
So we need new tools. You mentioned variational analysis.
Exactly. We need concepts from variational analysis and non-smooth optimizations. Like we need a specialized mathematical radar, or maybe sonar, to navigate this complex, potentially non-smooth, constrained landscape.
Okay, let's build up that toolkit. Before stating the core assumptions, particularly that KL condition, we absolutely have to get the notation straight. Let's start with the basic sets and some key properties.
All right. First, the domains. We define $6 as the domain of the function px, so $6 textum py, and dollars is the domain of ti do, so 2i style text in pg. These are the underlying spaces where any dollars live.
And there's a really important assumption made about right away in assumption 1, part 2. They assume dollars is compact. Why is compactness so critical here? What does it buy us?
Compactness is huge. Remember, compact means closed and bounded in Euclidean space. It guarantees several fundamental things. First, it ensures that the inner maximization problem, max y, actually has a solution for any fixed $6. The maximum is attained. Without compactness, the max might not exist. It might go off to infinity.
Okay, existence of the maximum. What else?
Second, it allows us to define finite bounds on various quantities, which are absolutely necessary inputs for the eventual complexity analysis.
Oh.
Specifically, because dollars is bounded, we can define d dollars the maximum possible distance between any 2 points in dollars. It's the diameter of dollar.
A finite diameter.
And we can define m col as the maximum variation of the convex function, ta col over the compact set dollars. Since colors is continuous, being convex and finite on its domain, n dollars is compact, ta must be bounded on AF, so its variation is finite.
And why are these finite bounds dealer and EM already needed later?
Because when we analyze how fast the algorithms converge, the convergence rates and the number of iterations will explicitly depend on these constants. If they were infinite, we couldn't prove finite time convergence. The complexity bounds would blow up. So compactness of dollars is a foundational assumption for getting concrete complexity results.
Makes sense. Compactness provides essential boundedness. Now, what about the actual feasible set for the inner player Gore?
That's denoted by the place. It's the intersection of the domain dollars and the region satisfying the constraints. The set, this is where the maximizer, Yeller, must actually live. Since the dollars is compact and Su is smooth, hence continuous, the set is closed. The intersection of a compact set and a closed set is compact. So Zul is also compact.
Good, so the feasible set $0 inherits compactness. Now let's move to the functions themselves. They define a combined function revision y to represent the entire inner objective, including the constraint.
Yes, this is a neat way to package the inner problem.
Yeah.
They define delta C FSY. Let's talk about that last term. Delta C 0y, that's the indicator function, right? What's its role?
It's a standard device in optimization, especially convex analysis, to handle constraints. The indicator function for a set of letters is defined as it's 0 if $0 is in the set dollars, and it's plus and 50 if $0 is outside the set dollars.
Ah, but here we have a maximization problem, and it's subtracted. So it's 0s of 2i's and n50 of cy.
Exactly. So by subtracting this indicator function, they've essentially encoded the constraint, lira y, directly into the function 5 stels y. If var satisfies the constraint, the term is 0 and doesn't affect the value. If u violates the constraint, the term becomes n50, making that automatically non-optimal for the maximization. Clever. So maximizing 5x over all of your dollars is equivalent to maximizing 5xy just over the feasible set seller.
Precisely. It absorbs the constraint into the objective. This function, 5xy, represents the complete inner problem objective.
Okay, so we have 5xy. Now, how do we get to the function we ultimately want to minimize?
We define the maximal function, often called the value function of the inner problem. It's denoted phi x hours. It's simply the result of that inner maximization. For any given 6-hash gives you the best possible value the inner player can achieve.
And this fx stellar is the function the outer player sees.
Almost. The total objective function that the outer player is nice to minimize is 5x. This combines the maximal function phi of x with the simple convex term phi x plus pxx. Our ultimate goal in this whole setup is to find a point, $6, that is an approximate stationary point or an approximate local minimum of this potentially very complicated function.
Complicated because for the result of a maximization of a non-convex, non-concave function over a constrained set is likely to be non-smooth and non-convex itself. Right?
Exactly. Even if 4 does a smooth, the act of taking the maximum introduces non-smoothness. Think of the max of 2 lines that has a kink. 4 will generally have kinks or corners, meaning its gradient might not exist everywhere. And it will generally be non-convex. This is why we need the tools of non-smooth analysis.
Right. This brings us to the definitions of the differential objects. We can't just rely on the standard gradient to $. We need something more general.
Correct. For the parts that are smooth, like 4 itself, we still use standard notions. The paper assumes 4 is smooth. This is the standard Lipschitz continuity of the gradient. Oldable list where cells and total gross is once there. This just means the gradient doesn't change infinitely fast. Loadable is the Lipschitz constant.
But they also mention Holder smoothness. What's that?
Holder smoothness is a generalization. It relaxes the Lipschitz condition slightly. A function dollar has Holder smooth gradient with exponent 0, 0, and constant arif. L blich EZ2. If whole of any1, this reduces to standard Lipschitz smoothness. But allowing Dorg, it covers functions whose gradients are continuous, but maybe not Lipschitz continuous.
And why introduce this generalization? Does it come up later?
Yes, crucially. As we'll see, the KL conditioned assumption later on will imply that the maximal function Eller might only be Holder smooth, not necessarily Lipschitz smooth. So they need this definition up front to precisely characterize the properties of Kato. The exponent will actually be determined by the KL exponent data.
Okay, foreshadowing noted. Now, for the non-smooth parts, especially in functions involving indicator functions or the max operator, we need subdifferentials.
This is where we transition from classical calculus to variational analysis, the calculus of non-smooth functions. The gradient is replaced by the concept of a subdifferential, denoted by partial. The subdifferential partial fis at a point $6 is generally a set of vectors, not just a single vector like the gradient. These vectors generalize the notion of slope or gradient direction.
The paper defines 2 types, the regular subdifferential and the limiting subdifferential. Let's start with the regular one, Freck-Verhoffer.
The regular subdifferential, or Frechet subdifferential, is defined based on tangent cones and normal cones, or equivalently, via a limit involving the function values. A vector for v Frecklo x $0. Intuitively, this means the linear function defined by $1 locally underestimates the function at $6. For convex functions, it coincides with the standard convex subdifferential. For smooth functions, it contains only the gradient.
Okay, that seems like a direct generalization of the gradient condition. But then they introduce the limiting subdifferential partial form. Why the need for another one? What's the issue with the regular subdifferential?
The issue is that the regular subdifferential point can be too small or even empty at some non-smooth points. This makes it difficult to use for proving things like optimality conditions or convergence, because the set might not contain the information we need or might not behave well under limits.
Too small. How can it be empty?
Consider a function like Boraforn at $6. The function has a sharp peak. The regular subreferential form is empty. There's no single linear function that locally underestimates it.
Ah, okay. So the regular subdifferential isn't robust enough for all cases. How does the limiting subdifferential fix this?
The limiting subdifferential, or Kurdyka-Ło subdifferential, partial fix, is defined as a limit of regular subdifferentials from nearby points. Formally, by lexigi, vk to svk to fix, vk to vk, vk exists to fk. Basically, you look at all sequences of points 6k converging to $6, where the function values also converge. You take your regular subgradient vk at each 6. If these vk's converge to some vector, then vk belongs to the limiting subdifferential partial fix.
So you're sort of filling in the gaps by looking at the limits from nearby points where the regular subdifferential might be better behaved.
Exactly. This limiting process makes the limiting subdifferential partial fix a much more robust object. It's always a closed set, possibly empty only if the function is plus infinite at 30-day. For convex functions, it still coincides with the convex subdifferential. For smooth functions, it's just the gradient. For that Zhaosong example, the limiting subdifferential partial fitch is the interval $1, which captures the slopes from both sides.
Got it. So partial phase is the workhorse subdifferential for general non-smooth functions because it's mathematically well behaved and captures the necessary local slope information even at tricky points. This is the one we'll mostly use when talking about stationarity for physis.
Precisely. It's the primary tool for analyzing non-smooth, non-convex functions like our textile.
Okay, subdifferentials defined. Now, how do we measure stationarity? If the gradient is 0 for smooth problems, what's the equivalent here? The paper mentions slope and limiting slope.
Right. Since the subdifferential partial phase is a set, we can't just say, is it 0? Instead, we often look at the distance from the 0 vector to this set. This measures how close the subdifferential is to containing the 0 vector. If $0 in partial phase, the point 6 is called a limiting stationary point.
And the slope concepts. And phase.
These are alternative but closely related ways to characterize ascent or stationarity, especially useful in the context of the KL condition. The slope collar is defined as fractal fix. It measures the maximum instantaneous rate of increase from sexy. If dapla is differentiable, it's just bapla.
And the limiting slope, another limit.
Yes, the limiting slope is defined as the limit inferior of the slopes at nearby points. Limit fixt, it provides a more stable measure of the steepness around 6 pi's.
These seem quite technical. What's the payoff? How do they relate to the subdifferential distance?
The connection is made clear in lemma 4 of the paper, which summarizes key properties. For our purposes, the most important part is lemma 4i. It states that for a function phi that is lower semi-continuous, which our seller will be under standard assumptions, the limiting slope is equal to the distance from 0 to the limiting subdifferential. The limful fix, assuming the function is finite at x.
Ah, okay. So the limiting slope gives us exactly the standard measure of stationarity for non-smooth functions, texture 0, partial. Finding a point $6 where this limiting slope is small, close to 0, is equivalent to finding an approximate limiting stationary point.
Precisely. It provides the measure we will use for our stopping criterion. We want to find an $x such that $x is less than some small tolerance epsilon. This rigorous setup allows us to handle the non-smoothness inherent in X-Man.
Excellent. That lays the groundwork. We have the problem structure, the key functions for awares, and the necessary tools from non-smooth analysis like limiting subdifferentials and limiting slope. Now we can finally tackle the core assumption.
Yes, now we can move into section 2. The power of the local Kurdyka-Ło KL condition. This is really the heart of the paper's theoretical contribution.
And it's assumption 1, part 4. This assumption is the geometric cornerstone, the foundational bet that allows Liu and Wang to prove convergence rates for their algorithms in this difficult setting.
That's right. But very importantly, they don't apply the KL condition directly to the original inner function v over xy that we defined earlier.
Oh, why not? What do they apply it to?
They introduce a novel lifted minimax problem. They add an auxiliary variable, let's call it Zeller, and define a new lifted inner function v over xy and a related surrogate constraint dual Lisker's y. The KL condition is then assumed to hold for this lifted function v over x in color with respect to the inner variables.
Okay, hold on. Lifting, auxiliary variable Zeller, surrogate constraint pi to the Romer. We need to understand why this lifting is necessary before we even look at the KL definition itself. What problem does introducing Zeller and this VOV solve?
This is a really crucial and perhaps subtle part of their approach. Remember, algorithm 1, the sequential convex programming SCP method they'll use for the inner problem. SCP works by iteratively solving approximations of the original problem. Specifically, it approximates the non-concave parts and the constraints. For the constraints, this restores evil. A standard technique in SCP is to replace them locally with a convex approximation. Here, they use a specific type of convex surrogate based on a quadratic approximation around some point. Let's call that point Zivri. The surrogate constraint for the JIRA original constraint, C or YZ or angle, looks something like this, defined in equation 11, where Lipschitz constant with a gradient of C jur y is always an overestimate of C jur y, meaning WI C jur y. It's a convex upper approximation.
Okay, so Z-wire is a stricter condition than the original SWI.
Potentially, yes. The key is that convex inia for a fixed zia. Now, as standard SCP, you'd pick the current iterate ia as the point zia for the approximation in the next iteration. But Liu and Wang do something different. They make C-ray an independent optimization variable in the inner problem.
How does that work? What's the lifted function, 5yz, defined in 12?
It looks like SYZ. Compare this to SY. SYZ. They replace the original indicator function del C with the indicator function for the surrogate constraint.
But now the constraint depends on S.
Exactly. And the inner problem becomes maximizing 5z over both big and z, where some highs are in the original domain FASB.
Why is this helpful? Why optimize over z, the point of approximation?
It seems to be a theoretical device that facilitates the analysis, particularly connecting the SCP subproblem structure to the KL condition. By making z a variable, the inner problem implicitly chooses the best point z around which to approximate the constraints z, y, z. This lifted formulation, FASYZ, turns out to have the right structure for the subsequent analysis, particularly for relating the KKT conditions of the SCP subproblem, which naturally involve Liz, to the properties derived from the KL condition on FASV.
Okay, it's a structural choice to make the analysis cleaner. But does maximizing this new failure give the same result as maximizing the original values? We need them to be equivalent.
Yes, and that's the content of lemma 3. It proves the critical equivalence. Maxi Fy Xy Z S X. This means that analyzing the lifted problem with phi is mathematically equivalent to analyzing the original problem with $5.
Yeah.
The lifting doesn't change the optimal value.
Yeah. Okay, so the lifting is valid. We are now trying to minimize SIFX plus PX, which is the same as our original values. And the core assumption, assumption 1, is that this lifted inner function, 5 back y, satisfies a local KL condition with respect to the inner variables, yiza up.
Correct. Now we can finally look at the KL definition itself, inequality 15. For a fixed ones, the KL condition states that there exist constants $, temma 0, demas nec, and sigma gaze 0 xy dollars and dollars, such that the following inequality holds. But it doesn't hold everywhere. It only holds for pairs that belong to a specific level set.
Okay, let's break down that inequality first. The left side, x, y, z, that's the suboptimality gap, right? How far the current value x, y, z is from the maximum value factor.
Precisely. It measures how much potential improvement is left in the inner maximization for that fixed Chema set.
And the right side, textivis since yz semba, that's our measure of stationarity for the inner problem with respect to damas nefast. It's the magnitude of the slope or subgradient for the inner variables.
Exactly. So the inequality is relating the suboptimality gap to the stationarity measure.
And it's raised to the power theta. What does that exponent theta mean intuitively?
Theta captures the sharpness of the function near its maximizers. Think of it like this. The inequality says that the slope, right side, must be lower bounded by some function of the gap, left side, specifically slope c times.
If theta 12.2, this means slope z-score. This condition is known as the Kurdyka-Ło condition. It implies that if you're not optimal, gap 0, there must be a significant slope pushing you towards optimality. It prevents the function from becoming too flat near the maximum. If theta is closer to 1, say theta is neighboring 9, then slope t times. Since theta is much smaller than theta when the gap is small, this is a weaker condition. It allows the function to become flatter near the maximum.
So theta 12.2 is the strongest case covered here, sharpest geometry. And as theta approaches 1, the condition gets weaker, allowing flatter landscapes near the optimum.
Exactly. The PL condition is known to be weaker than strong concavity, but still strong enough to guarantee nice properties like linear convergence for some algorithms. By allowing theta to be in the range $12, Liu and Wang are generalizing significantly, covering a much broader class of potential geometries for the inner problem.
Okay, now what about the local part? The inequality only holds for del z in the level set defined in 16. What is $?
The level set contains pairs that are close enough to being optimal for the inner problem, but not exactly optimal. Specifically, del z in yz a x x y z, where the threshold delta x is depends on the outer problem stationarity, where the threshold delta depends on the outer problem stationarity. Delta x delta sigma.
Whoa, okay. So the region where the KL inequality for the inner problem 5 must hold depends on how close the outer variable 6z is to satisfying its own stationarity condition for 2y. That seems complicated.
It is, but it's crucial. Let's unpack the parameters, gamma dollar and sigma Josh. They define the scale of this locality. Delta x defines an upper bound on the inner suboptimality gap for which the KL condition is required to hold.
How does this behave? Let's consider remark 1 in the paper.
Remark 1 gives the intuition. When sigma dollars is far from being a stationary point of the outer problem, then sigma is large. If sigma dollars, then delta is also large. This means the level set dash includes points with potentially large suboptimality gaps. In this case, the KL condition is relatively easy to satisfy. It just needs to hold over a wide range of inner points.
Okay, far from the outer solution, the inner KL condition is less demanding.
But as the outer algorithm makes progress, sig$ gets closer to a stationary point, so Texas x becomes small. Then delta also becomes small. The level set shrinks, now only containing inner points that are very close to optimal. Very small gap. The KL inequality must now hold specifically in this shrinking region, very close to the inner solution set.
So the geometric condition becomes more restrictive, precisely where we need it most as we approach a solution to the overall minimax problem.
Exactly. It's a condition about the local geometry near the optimal set of the inner problem, conditioned on the outer variable $6 being close to its stationary points. It's a sophisticated way to assume just enough geometric regularity precisely where it matters for proving convergence, without needing a strong global condition like strong concavity.
So the KL condition isn't some magic bullet that holds everywhere. It's a statement that the optimization landscape isn't pathological locally in a way that's linked across the inner and outer problems.
Yes, and assuming this local KL condition holds for the lifted inner problem is the key analytical leap. It's what allows them to bridge the gap between the complex, constrained, non-concave inner problem and the possibility of proving complexity guarantees for an algorithm solving the outer problem.
All right. Assuming this local KL condition holds, what does it buy us? What are the theoretical consequences? The paper presents two major ones, Theorem 1 and Theorem 2. Let's start with Theorem 1. Local Holder smoothness of fascicants.
This is the first big payoff. It shows how the assumed geometry of the inner problem, via KL on 5, dictates the analytical properties of the outer problem's objective component, which equals 5. Theorem 1 essentially proves that if the lifted inner problem satisfies the local KL condition with exponent theta, then the maximal function behaves nicely. Specifically, it's differentiable, and satisfies a local holder smoothness property on a relevant set of fascicants.
Differentiable? I thought phi x was generally non-smooth.
It is generally non-smooth globally. But Theorem 1 shows that within a certain region, one salon, related to the target accuracy, exicons, is differentiable. And even better, its gradient mabla fscos satisfies a holder continuity condition.
Okay, let's look at that condition. Inequality, 18. It bounds the change in the gradient. Nabla FC, nabla FC.
Looks like this. The first term, nabla effects, comes from the assumed smoothness of the original function feller. That's standard. The second term is the crucial new part derived from the KL condition. It's a holder term with a specific exponent fella.
And that exponent nu depends directly on the KL exponent theta. Let's trace that dependence.
If theta takes 12, the PL case, strongest geometry, then Nebel. Well, let's trace that dependence. Added to the first term, it just means Nebel FFC is Lipschitz continuous locally. So PL condition implies local Lipschitz smoothness of Thelen weak.
Nice. And if theta gets closer to 1, weaker geometry, say theta x was $34.3.
Then 134 and 34, the bound becomes like 34 and rod. This is older continuity, but weaker than Lipschitz. As theta, 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 the function becomes less and less smooth, closer to just being continuous.
Wow, so there is a direct quantitative link. The sharpness of the inner problem's geometry near its optimum, measured by theta, dictates the degree of smoothness of the outer problem's objective function measured by theta.
This is a massive analytical result. It connects the geometry KL to the analysis smoothness. It tells us that even though theta comes from a complicated, constrained, non-concave maximization under the KL assumption, it still retains a quantifiable amount of smoothness locally. And the amount of smoothness is determined by the KL exponent theta.
And why is knowing this local Holder smoothness so important?
Because many optimization algorithms, particularly proximal gradient methods, have convergence guarantees that depend on the smoothness properties of the objective function. By establishing this local Holder smoothness with the exponent determined by theta, Theorem 1 paves the way for applying an inexact proximal gradient method, algorithm 2, to minimize fx plus p get s's, and crucially, to derive complexity bounds that depend explicitly on a theta. Okay, so Theorem 1 provides the necessary smoothness property for the outer algorithm's analysis. What about the second consequence, Theorem 2, local growth property? Theorem 2 shows that the KL condition on phi-s also implies a useful property about how the original inner function phi-s grows as moves away from the set of inner maximizers. Specifically, for any Euler in that same local level set, redefined appropriately for phi instead of phi, we have fxy, where θ1 phi is some positive constant, and fx is the set of points that achieve the maximum phi.
Let's translate that. The suboptimality gap, val of x, is bounded below by the distance to the optimal set, raised to some power.
Yes. The exponent is 1 ala 1 theta. Since theta in 12, 1 theta is greater than or equal to 2. If theta 12 2, the exponent is 2, meaning we have quadratic growth. The gap grows like the square distance. If theta is closer to 1, the exponent 1 ala 1 theta becomes very large, meaning the growth is much slower, much flatter.
And why is this growth condition useful?
This is essential for analyzing the convergence of the inner loop algorithm, algorithm 1, the SCP method. When we run an iterative method to approximate the inner maximum of the vol of x, we need to know that making progress in terms of function value actually corresponds to getting closer to the true solution set. This growth condition provides exactly that link. It guarantees that reducing the suboptimality gap forces the iterate dollar to move closer to an exponent at a predictable rate, determined by theta.
Can you give a sketch of how they prove this growth property from the KL condition? The paper mentions lemma 5.
The idea, roughly, comes from constructing an auxiliary function, like Cs syz 1 theta. They use the KL inequality 15 to show that the slope of this function dollars is bounded below by a constant theta. Then, using properties relating the slope of a function to how fast the function grows, related to the concept of error bounds, they can integrate this slope information to get the relationship between the function value gap, phi, which is related to gy, and the distance to the optimal set, text yzx. This then translates back to the growth condition stated in Theorem 2 for the original phi-x.
Okay, so it involves constructing a potential function based on the KL exponent and using calculus-like arguments involving slopes and integration to get the error bound or growth property.
That's the essence of it. The KL condition's power is that it provides just enough structure, relating gap to slope, to allow these kinds of arguments, leading to both the Holder smoothness of Theorem 1 and the growth property for Fourier Theorem 2. These are the two pillars supporting the subsequent algorithmic analysis.
Fantastic. That gives us a solid understanding of the theoretical landscape shaped by the KL assumption. Now, let's get practical. How do we actually solve the problems? We need the algorithms.
Exactly. We need the mechanics. First, we need an efficient subroutine to handle the inner maximization problem, maxi fxy, or equivalently, minimizing the lie kk. Remember, this is potentially non-concave, so the law is non-convex, and subject to complex constraints, CTOHX. This is where algorithm 1 comes in.
Algorithm 1, the SCP method, sequential convex programming. Let's walk through it. The context is solving problem 24 in the paper. where G and G sum plus G plus Kd is the potentially non-convex smooth part, and Kutue is the simple convex part. They use the Zia as the variable here, which matches our Ja from before.
Right. SEP tackles this non-convex constrained problem by solving a sequence of convex constrained subproblems. It's an iterative method. Let's say we're at iteration $. With the current feasible solution $60. How do we find the next iterate zk plus 1 down?
This is where the engineering seems to meet the math. How does SCP take this fundamentally non-convex constrained problem and make it tractable at each step? What's the subproblem it solves?
At step Day, SCP constructs a convex approximation of the objective Galanga day around the current points K, and it uses the convex surrogate constraint, Gande, that we discussed earlier. The subproblem given in 27 looks like this. Find ZK plus 1 deck. They use an inner loop index Day for line search. Let's ignore that for a moment. Think of it as finding Dia by solving. Quad band day is left wrangled egg plus column to LG ace day dale plus Q, right?
I've written the first term slightly differently to emphasize it's approximating Dirichlet around ZAC, plus the GK constant doesn't affect the Arkman.
Okay, let's break down the components of this subproblem, objective and constraints. What transformations are happening here compared to the original problem in HETD day?
There are 3 key transformations happening simultaneously. 1, linearization of the non-convex part. The potentially non-convex smooth part, GZ, is replaced by its first-order Taylor approximation around ZK, plus Langle-Nabla, ZCK, ZZK, Wrangle-Nabla. Since GCK is constant, minimizing this is equivalent to minimizing Langle-Nabla Wrangle. This turns the non-convex part into a linear, hence convex part. 2, quadratic regularization. A proximal term for x squared O is added. This is crucial. It adds strong convexity to the subproblem objective. Lang-Plevo is a parameter related to Lipschitz constants chosen large enough to ensure progress. This regularization guarantees the subproblem objective is strongly convex, which means it has a unique minimizer and is well behaved. 3, surrogate constraints. The original potentially complex constraints are replaced by the convex surrogate constraints, Ling-Slagolaba. We already know it's convex in Zia.
So the subproblem is minimize linear term plus strong quadratic plus simple convex subject to convex constraints. So that entire subproblem is now a strongly convex constrained optimization problem.
Precisely. And strongly convex constrained problems are much easier to solve, often efficiently using standard solvers, like interior point methods or active set methods, depending on the structure. SCP cleverly transforms the hard original problem into a sequence of tractable convex subproblems.
Okay, so we solve this convex subproblem to get candidate direction or point. Let's call the solution Z sub, EZK plus 1, E sub.
Not necessarily. We need to ensure we actually make progress on the original objective as E. This is where the line search comes in, lines 5, 7 in algorithm 1. They compute a candidate point, ZK plus 1I, potentially based on Z sub, and check if it provides sufficient decrease into dollars. The condition is ZK plus 1I plus 1, where dollar is some positive constant. This condition demands a decrease in the objective that's proportional to the squared step size.
Y squared step size.
This type of sufficient decrease condition is common in proving convergence rates for optimization algorithms, especially in non-convex settings. It ensures that we're not taking minuscule steps that make vanishingly small progress. If the condition isn't met, they typically increase the quadratic penalty parameter, making the step shorter and more conservative, and resolve the subproblem. That's the inner loop index $1.
And Theorem 4 in the paper guarantees that this line search procedure, increasing all odds, will terminate in a finite number of steps.
Yes, Theorem 4 proves that the line search finishes quickly. This ensures that each main iteration dollars of the SCP method is computationally efficient.
Okay, so SCP iteratively solves convex subproblems and uses a line search to guarantee sufficient decrease on the original non-convex objective. For this whole process to be reliable, especially with those surrogate constraints, we probably need some guarantees about the original constraints themselves, right?
Absolutely. This is where assumption 2 comes in. The Mangasarian-Frumovitz constraint qualification, or MFCQ.
MFCQ. That sounds important. What does it guarantee?
MFCQ is a condition on the geometry of the feasible set. Think of it as a check that the boundary of the feasible set isn't pathological at any point. Formally, MFCQ holds at a feasible point if the gradients of the active constraints at 7 law, those used for which 7-day jaw are linearly independent, or more generally, if there exists a direction epure such that Langle CJJ jaw wrangle dollars for all active constraints is 0.
What does that direction dollar mean intuitively?
It means there's a direction you can step in from zero that points strictly into the feasible region, satisfying all active constraints simultaneously with some margin. It prevents the feasible region from collapsing into a lower dimensional shape or having sharp outward-pointing corners where you get stuck.
So MFCQ ensures the feasible region is regular enough locally. Why is this needed for the SCP algorithm?
It's crucial for ensuring that the surrogate constraint lid is a good and useful approximation of the true constraint. Specifically, MFCQ, assumed to hold uniformly over $, guarantees the result in Theorem 3. Theorem 3 says there exists a constant zeta $, such that for any feasible CK, there's a point Y satisfying the surrogate constraint $.
Meaning the feasible region defined by the surrogate constraint isn't empty and actually contains points strictly satisfying the condition.
Yes, and this constant zeta quantifies how strictly it can be satisfied. This is vital because it ensures that the convex subproblem, using Lie, always has feasible solutions that allow the algorithm to make progress, both in terms of feasibility for the original theater and optimality for $. Without MFCQ, the surrogate constraints might become inconsistent or might prevent the algorithm from finding good steps.
And this MFCQ regularity has another critical consequence mentioned in Lemma 1, bounding the Lagrange multipliers.
Exactly. When we solve the convex subproblem 27, the solution to k plus $1 comes with associated Lagrange multipliers, lambda, corresponding to the surrogate constraints. These multipliers represent the price or sensitivity associated with each constraint. Lemma 1 provides a crucial uniform bound on the L1 norm of these multipliers. Let's unpack that bound to $. It depends on the Neller, so if the constraints are more regular, larger zeta, the multipliers are better bounded. What are the other terms?
$' is an upper bound on the gradient norm. Dollars is the diameter of the domain. The bar is related to the Lipschitz constants like Laur and null Bay, and Nimhals is the maximum variation of dollars. All these quantities are finite because phi is smooth, the chi is convex, dollars is compact.
So the critical insight is that MFCQ, via zeta, ensures that the Lagrange multipliers generated by the SCP subproblems remain uniformly bounded throughout the algorithm's execution, independent of the dollars. Yes, this is a monumental result for the analysis. Unbounded Lagrange multipliers can lead to numerical instability and great convergence proofs. Bounding them by a Lie dollars is essential for proving the stability and convergence rate of the overall SCP method.
Okay, we have the SCP mechanism, the guarantee of sufficient decrease, and the stability provided by MFCQ and bounded multipliers. Now, how do we connect this back to the KL condition to actually prove convergence of algorithm 1 for the inner problem?
This is the job of Lemma 8. It links the output of one step of the SCP method back to a stationarity measure related to the KL condition. Remember, the KL condition assumption 1.4 was defined on the lifted function phi xyz, or equivalently, minimizing hate xyz ok xy. Z op 8 shows that the step zk plus 1z's get taken by SCP provides a bound on the stationarity measure for binates, specifically XST lay, partial z plus 1z, what's op z opos. The subdifferential here is with respect to both YL and zp evaluated at zok plus 1c.
So the distance to stationarity for the lifted objective is controlled by the size of the step taken by the practical SCP algorithm. What is the mega?
Mega is a constant that bundles together all the relevant Lipschitz constants, the Laplace theta bound on the Lagrange multipliers $, and the proximal parameter Lieferstahl. The exact expression is given in 33. Since all these components are bounded, no mega is a finite constant.
Okay, so we have two key relations now. One, sufficient decrease.
Nice.
Enough so, partial Hijit plus 1 ziga plus 1 ziga.
And we also have the KL condition assumption for hero, partial ants yz, partial a the zeta $. Rewriting 15 for the minimization $, where hero is the minimum value.
How do these pieces fit together to give a convergence rate in Theorem 5?
You combine them. The sufficient decrease gives you a bound on skull plus 1 skull in terms of the function value decrease. The stationarity bound relates the skull plus 1 skull to the subdifferential norm. The KL condition relates the subdifferential norm back to the function value gap, per, which is related to Tazel. Putting these together through careful algebraic manipulation, details in Lemma 9 and Theorem 5 proofs, allows you to show that the suboptimality gap HO decreases at a specific rate.
And that rate depends crucially on the KL exponent theta zaganon. What are the results?
Theorem 5 shows that algorithm 1 terminates in a finite number of iterations, let's call it k theta, to reach a desired accuracy tau for the inner problem, meaning finding theta such that some stationarity measure is less than tau. The rate of convergence, and thus k theta, depends directly on theta, case 1. Case 1, theta talti pk PL condition. The convergence is geometric or linear. The error decreases by a constant factor less than 1 in each iteration, like $1 for some alpha day. This is very fast. K theta will depend logarithmically on $1 case 2, weaker hey theta. The convergence is sublinear, specifically polynomial decay. The error decreases like 12. Theta will depend polynomially on $1 with the exponent depending on theta. The exponent $2 goes to infinity, meaning convergence becomes much slower.
So algorithm 1, SCP, is guaranteed to find an approximate solution to the inner problem in finite time, and the time it takes is explicitly quantified by the geometry of the inner problem via the KL exponental.
Exactly. This is a powerful result. It shows the SCP method is not only practical but also theoretically sound, with a convergence rate dictated by the problem's intrinsic structure. It's fast enough and reliable enough to serve as the inner loop solver for the main algorithm.
Perfect. We have a working, analyzed engine for the inner maximization. Now let's put it all together. Section 4. The outer loop. Inexact proximal gradient, algorithm 2, and the final complexity results.
Right. Now that we have a way, algorithm 1, to find an approximate solution y$ to the inner problem xc fsky for any given 6k, we can finally tackle the outer problem, fx plus pxa.
And the tool for this is algorithm 2, described as an inexact proximal gradient IPG method. Why IPG?
Proximal gradient methods are well suited for minimizing composite objectives like fxx plus pxa, where $5 is relatively smooth, at least locally Holder smooth, thanks to Theorem 1, and pst is simple convex, meaning its prox operator is easy. The inexact part comes from the fact that we can't compute the gradient of 5 exactly.
Why can't we compute fxt exactly?
Well, recall from Danskin's theorem or similar results. If y(sk) is the unique maximizer for the inner problem at 6k, then y epsilon x fsk, but finding the exact maximizer yk is generally impossible, especially since the inner problem is nonconcave and constrained. Algorithm 1 only gives us an approximate maximizer. Let's call it xkr.
So the inexactness comes from using the gradient in the approximate solution instead of the true one. We use my nabla x fk sk dollars as an approximation for nabla fk.
Precisely. That's the core idea of inexact gradient methods. We use an approximation of the gradient, but we need to control the error introduced by this approximation.
Okay, let's look at the main update step in algorithm 2, line 4. How does it calculate the next iterates xk plus 1?
It performs a proximal gradient step, but with 2 important modifications. The update is $ask plus 1 xk plus 1b sk2 plus prs. Again, I've written the first term slightly differently, but it leads to the same sexk plus 1s as minimizing the expression in the paper's line 4, ignoring constants.
Okay, this looks like a standard proc gradient step for minimizing approximated fsk plus p, but with 2 key differences we need to unpack. The adaptive step size parameter p and the constraint sex for bxk. Let's start with break bar. Why is it adaptive and how is it calculated?
The step size parameter bar p, which acts like $1 text step size, needs to be carefully chosen because Frite isn't necessarily standard Lipschitz smooth. It's only locally Holder smooth with exponent theta, according to Theorem 1. Standard proximal gradient analysis relies on Lipschitz smoothness.
So BARC needs to account for this weaker Holder smoothness.
Yes. The paper defines Dewey equation 38 based on the original Lipschitz constant load at the row, and also terms involving the Holder smoothness constant and exponent from Theorem 1, which depend on theta, c, and nabla, and the current stationarity measure. It's an adaptive parameter that essentially ensures the quadratic term xk is large enough to dominate the error coming from the Holder continuity term, guaranteeing that the expression inside the Dew is a valid upper bound for the true objective locally.
That sounds complicated but crucial.
Yeah.
It's adapting the step size based on the estimated local smoothness derived from the KL exponent in theta. Now, what about the constraint 6 exons in bxk? Why restrict the update to a ball of radius dollars around the current part?
This is directly related to the local nature of the key results. Remember Theorem 1. The Holder smoothness property for Theorem $ is only guaranteed to hold locally within a specific neighborhood, 1 epsilon, whose size depends on the target accuracy, epsilon, and the local KL parameters, gamma, sigma.
So the ball constraint is there to keep the algorithm operating within the region where our theoretical guarantees, like Holder smoothness, actually hold.
Exactly. The radius $ is defined explicitly in algorithm 2, line 2, as frac gamma epsilon sigma 4, assuming delta 1, as in the complexity analysis. Notice it depends on the target accuracy epsilon and the local KL parameter sigma sigma. By restricting the step 6k plus 1 to be within distance $3, they ensure that the analysis based on Theorem 1 remains valid throughout the algorithm's execution. It prevents the iterates from potentially jumping outside the region where the crucial smoothness property holds, which could happen if tart behaves wildly further away.
So the adapted ball handles the non-Lipschitz smoothness, and the radius dollar handles the locality of that smoothness. What links this outer loop back to the inner loop, algorithm 1?
The connection happens in line 5 of algorithm 2. After computing the new outer iterate 6k plus $1, the algorithm calls the inner loop solver, algorithm 1 SCP, to find the next approximate maximizer UK plus $1 for the inner problem at 6k plus $1.
And critically, the accuracy required from algorithm 1 isn't constant. It depends on epsilon and the KL parameters, right?
Yes, that's vital for the overall complexity. The stopping criterion talk plus 1 used for algorithm 1 when computing AK plus 1 is set dynamically. Details around lemma 10. It's chosen carefully to ensure that the error in the next inexact gradient, AK plus 1, EAK plus 1, is small enough.
Small enough for what?
Small enough so that it doesn't disrupt the convergence of the outer IPG method. Lemma 10 provides the guarantee. If the inner loop, algorithm 1, is run with a sufficiently small tolerance talk, plus 1 which depends on epsilon, theta, sigma, then the resulting inexactness in the gradient used in the next outer step is adequately controlled, allowing the outer loop theory to hold. This explicit coupling of the required inner accuracy talk to the desired final outer accuracy epsilon is what makes the final total complexity analysis possible.
It's like the outer loop tells the inner loop, okay, I need you to solve your problem, but you only need to be this accurate for me to make progress towards my overall goal, epsilon.
That's a perfect analogy. The required inner precision adapts based on the outer progress and target accuracy.
Fantastic. We have the full algorithm now. An outer IPG loop, algorithm 2, using adaptive steps and a radius constraint, which calls an inner SCP loop, algorithm 1, with a dynamically set accuracy target. Now for the ultimate payoff, the complexity guarantees. Theorems 6 and 7.
Yes, this is where all the theoretical machinery KL condition, Holder smoothness, growth property, bounded multipliers, SCP convergence, IPG analysis comes together to provide an end-to-end guarantee. Theorem 6 gives the iteration complexity for the outer loop.
How many outer loop iterations KL does algorithm 2 need to find an epsilon or stationary point of beta, meaning roughly partial epsilon muscle within the radius $3?
Theorem 6 bounds the number of outer iterations. Let's call it kipsilon. The bound is roughly Kix-log factors, right? The logarithmic factors are related to log epsilon, but the dominant term is the polynomial dependence on $1 epsilon.
Okay, let's stare at that exponent. Focus theta, fraxilin pater. It depends on the KL exponent theta and the locality parameter.
Yes. The overall iteration complexity is determined by whichever of these two terms is larger. The first term, 1 theta, comes directly from the KL geometry. Is theta 2 leta, this term is 2. If theta 2 leta, this term blows up, reflecting the difficulty of the weaker geometry.
And the second term, sigma theta, what does that represent?
Recall that sigma controls how the size of the local region, where KL holds, shrinks as 6LL approaches stationarity. A larger sigma means the region shrinks faster, which can make the problem harder if sigma theta becomes large. This term captures the interplay between the locality scale and the KL exponent.
So the number of outer steps depends polynomially on $1 epsilon, with an exponent determined by the worst-case interaction between the KL sharpness and its locality scale.
Precisely. It quantifies how the geometry, as captured by assumption 1, dictates the outer loop's convergence speed.
But that's just the number of outer iterations. Each outer iteration involves calling the inner SCP solver, which itself takes multiple steps.
What about the total work? That's Theorem 7, right? The first-order oracle FO complexity.
Exactly. Theorem 7 gives the bound on epsilon, the total number of first-order oracle calls essentially, the total number of gradient evaluations of $5 across all inner and outer iterations needed to reach epsilon stationarity. This is often considered the true measure of computational cost.
And how does epsilon depend on epsilon theta sigma?
The results are broken down based on the eps. Case 1, case ln Thiel condition. The total FO complexity is case 1, epsilon 2 right, case 1, 2. If sigma 1, 2, case 1, 2. If sigma 1, this is epsilon 2, which is quite good. Comparable to complexity for strongly convex-concave problems or minimizing smooth non-convex functions. If sigma $1, the locality affects the complexity more, becoming epsilon. Okay, the PL case is relatively efficient. What about the general case? Case 2 to theta in 12. Weaker KL. Here, the complexity gets significantly worse. The exponent on $1 echelon becomes much larger. Case 2, epsilon left, theta 1 left, theta 1 theta not credited. Let's try to simplify that exponent a bit by combining the first part. Theta 1 theta plus theta 1 plus theta 1 theta 1 still looks complicated. Wait, looking at the paper's theorem 7 again, the exponent seems different. It's given as O less delta theta. Let's recalculate that first part. Theta 1 theta, theta 1, theta 1, theta 1. Let's recalculate that first part. Theta on the left, theta plus theta for theta 1, 1, theta 1 for theta 1, theta 1, theta 1, theta 1 plus theta 1. Wait, looking at the paper's theorem 7 again, the exponent seems different. It's given as, okay, let's reread theorem 7 very carefully. The bound involves the product of the outer iteration complexity, epsilon, and the inner iteration complexity, epsilon. The number of inner iterations depends on the required accuracy. Talk needs to be roughly proportional to epsilon's salinity of outer. The inner complexity scales like text theta in 12 $1. Combining these leads to the complex exponent in theorem 7. Let's focus on the structure. The exponent is roughly inner complexity scaling, outer complexity scaling.
Yes, the exact exponent is complex, but the key takeaway is that it depends strongly on theta, especially through terms like 1/11 theta and 1/12 theta. As theta approaches 1, these terms blow up, leading to a very high polynomial dependence on $1 epsilon.
So the weaker the geometry, larger the theta, the dramatically higher the computational cost to find an epsilon stationary point.
Absolutely. The theorem provides a precise quantitative relationship between the geometric difficulty, KL parameter sigma, and the computational effort, epsilon. This is the main theoretical achievement. A complete end-to-end complexity analysis for this challenging class of constrained non-convex, non-concave problems grounded in the local KL geometry.
It really demonstrates the power of leveraging that geometric assumption. They managed to convert this seemingly intractable problem into a structure solvable by a known, albeit modified, IPG method, and quantify the cost based on the geometry.
That's the core success. It's the first framework to achieve this for the constrained non-convex, non-concave setting under such relatively weak geometric conditions.
Okay, before we wrap up, let's briefly touch on the numerical validation. Did they test this in practice?
Yes, Section 5 presents numerical experiments. They constructed a test problem, equation 43, specifically designed to fit their framework. It involved a non-convex, non-concave function, syllables with interactions between $6 plus highly nonlinear exponential constraints for a 6y equation 44.
So a genuinely challenging instance. What KL parameters did they assume for the setup?
They actually chose parameters corresponding to the best case geometry covered by their theory. The PL condition, theta alpha power by 5, and they use a relatively small locality factor, sigma 0.1.11. They then ran algorithm 2.
And the results? Did the algorithm effectively minimize the objective?
The results in table 1 are quite striking. For instance, with problem dimensions 1 power n2 quant5 1, number of variables for xnr1, the average initial objective value was around 1.42. After running algorithm 2 to find an approximate stationary point, 6 epsilon, the final objective value dropped dramatically to about negative 579.71 on average.
Wow, that's a huge decrease. It definitely found a much better solution.
Indeed. It demonstrates that the algorithm is highly effective in practice at navigating this complex landscape and significantly reducing the objective function value, at least for the problem instance they tested under the favorable PL assumption.
Did they also check if the inner loop was working correctly? That the approximate maximizer of the epsilon was good enough?
Yes, that's an important check. They compared the true maximal function value, which would require solving the inner problem exactly, with the approximate value computed using the output 2 epsilon from the SCP inner loop. They found the difference was extremely small, confirming that the inexact gradient approximation based on the SCP solution epsilon was very accurate. This validates the effectiveness of the inner loop, algorithm 1, and the error control mechanism, lemma 10.
Excellent. So let's try to synthesize this whole deep dive. What's the big picture takeaway from Wang's work?
The big picture is that this research provides the first complete algorithmic and complexity framework for tackling constrained non-convex, non-concave minimax problems, a class that is fundamental to modern machine learning challenges like GANs and adversarial robustness. They achieve this by identifying the local Kurdyka-Ło KL condition as the key enabling geometric property.
And leveraging this KL condition applied to a novel lifted formulation of the inner problem.
They were able to prove crucial analytical properties, namely the local Holder smoothness of the outer objective function and a local growth condition for the inner objective. These properties then allowed them to design and rigorously analyze a two-loop algorithm. An inner SCP method, algorithm 1, for the constrained non-concave maximization, and an outer inexact proximal gradient method, algorithm 2, for the overall minimization.
And the culmination is explicit complexity guarantees, Theorem 6 and 7, that quantify the total computational effort required, showing how it depends directly on the geometric parameters of the KL condition and the desired accuracy epsilon.
Exactly. The math is robust because the guarantees rely on this verifiable geometric condition, KL, not on overly strong and often unrealistic assumptions like global strong convexity or concavity. It's a framework built on a more realistic geometric foundation.
It's fascinating how directly the complexity hinges on those geometric constants theta and sigma then, which brings me to a final thought. The current algorithm requires these constants to be known or estimated beforehand to set the step sizes, the radius, and the inner loop tolerance. That's true.
Assumption 1 feet assumes these constants exist and the algorithm uses them.
So since the performance depends so heavily on theta and sigma theta, but in practice you might not know their values precisely for a given real-world problem, what might be the necessary next step to make this approach even more practical? Could we get around needing to know theta and sigma up front?
That's a fantastic question, and it points directly towards a major challenge and opportunity in this field. The most critical next frontier, I believe, is the development of adaptive methods. We need algorithms that can somehow estimate these crucial geometric constants, theta and maybe sigma, dynamically during the optimization process itself.
How might that work?
Perhaps through techniques that probe the local geometry, maybe by observing the progress rate or testing function value changes against iterate changes. There's research in other areas of optimization on adaptive estimation of smoothness constants or KL exponents. Extending those ideas to this complex, two-level, constrained minimax setting would be a significant breakthrough.
So the provocative thought for you, our listener, is, could we build algorithms that learn the landscape's geometry as they navigate it? If we could develop methods that adaptively estimate theta and sigma, it would remove that final barrier of needing prior knowledge, potentially making this powerful theoretical framework applicable to a much wider range of practical, large-scale machine learning problems, where the exact underlying geometry is currently unknown.
That's the challenge. Making these theoretically powerful, geometry-aware methods fully adaptive and practical is likely where much future research will focus. Welcome back to The Deep Dive. Today, we are undertaking, well, let's call it a mission, into the absolute high frontier of mathematical optimization. We're going deep into the structure of what are known as constrained non-convex, non-concave minimax problems.
Sounds like a mouthful, right?
It is, and it really is the frontier. This is the math powering some of the most complex, cutting-edge machine learning systems today. You should think of the underlying mechanics of generative adversarial networks, GANs.
Right, Jan.
Or things like advanced adversarial training routines. And these problems are just, well, they're brutal because the objective function, it defies the standard assumptions we like, convexity or concavity.
And then they add constraints on top.
Exactly, complex constraints on top of that. It makes the whole thing incredibly challenging.
The rigor required to even analyze, let alone solve these problems seems immense.
It is, which is why our guide today is, frankly, a remarkable paper by Liu and Wang. They actually managed to establish reliable complexity guarantees in this otherwise, you could say, chaotic landscape. Okay, so that's our goal then, to unpack how they did that.
Precisely. Our goal for you, listening, is to understand the core insight, how they utilize the geometry of the problem. Specifically, they use a concept called the local Kurdyka-Ło condition, or KL condition for short.
KL condition, got it.
And they use this KL condition to transform what looks like an intractable problem into two solvable components. We're going to unpack the exact notations step by step and look at the two resulting algorithms they propose.
Which are?
An inner solver using sequential convex programming, and an outer method based on inexact proximal gradient. And the key is, these deliver actual complexity guarantees.
Okay, let's start right at the beginning then. The problem itself. They focus on this primary structure. Minimize X, maximize Y, but with constraints on Y.
Exactly. Let's write it out, or at least picture it. It's Minimize over $6, then maximize over y, where it must satisfy this function, y plus p size qy.
Right. So yx, y, that's the core interaction term.
That's the bedrock, yeah. It's smooth, which is good. But critically, it's generally non-convex in sectors and non-concave in yang.
And that's the fundamental difficulty, right? The non-convex, non-concave part. It means we don't have nice bowls or hills. We have this complex saddle point landscape.
Precisely. That's what makes minimax problems inherently hard. You're looking for a specific kind of equilibrium, not just a minimum or a maximum.
Okay, then we have px and 40i. What role do they play?
These are, let's say, the structured terms. They are assumed to be simple, closed, and convex functions. Think of them often representing regularization terms, like L1 penalties, maybe.
To encourage sparsity or something.
Exactly. Or they might just define the basic domain constraints for sex and hours. They add structure, but they're the easier parts compared to 5.
And the constraint, that's only on the inner variable dollars.
Yes, and that's a key focus here. Putties is a smooth mapping, so the constraints themselves aren't completely wild. But having any constraints on the inner maximization problem, SAS and hours, that's what really distinguishes their work.
Oh.
Well, a lot of the prior research focused heavily on unconstrained minimax problems. Just mix maxi Evertswile. Adding that sec up y makes solving the inner maximization, finding that best dollar for a given $6, much, much harder to do efficiently.
Okay, I see. Now, you might look at this form, this equation 1 in the paper and think, is this just some specific theoretical setup? But they argue it's actually foundational, right? Why is solving this particular form so important for broader problems?
Great question. It's because it directly relates to a common technique for solving more general constrained problems using what's called the penalty approach.
Oh, okay. You mean if you had constraints on both $6 and $?
Exactly. Suppose you had a problem like mid-cis, so constraints on both. A standard way to tackle that is using an exterior penalty method for the outer constraint.
You mean you move the de-Sixical constraint into the objective function with a penalty term? Like add $ times violations of it.
Precisely. You create a sequence of subproblems. In each subproblem, sex dollars becomes effectively unconstrained, or only subject to dxy, but you add a penalty that grows if dx positive. Meanwhile, the inner maximization still has its original constraints, cy $.
Okay, so you solve the sequence of problems that look like the form they study, equation 1, but with a modified y, or...
Essentially, yes. You have new makes dollars plus roca times to the odd times. And the theory says if you let these penalty parameters go to infinity, the solutions of these subproblems converge to the solution of the original doubly constrained problem.
I see. So if you can get solid complexity guarantees for their base form, equation 1...
then you can potentially apply that complexity analysis to the whole sequence of penalized subproblems. It provides a foundational building block for tackling that much broader class of problems.
That makes a lot of sense. You handle the difficult outer constraint using a penalty, keeping the difficult inner constraint explicit. So solving that inner constraint maximization efficiently is really the key challenge they need to address.
That's exactly right. The structure of wine isolates that core difficulty.
Okay, so if we're dealing with functions that are non-convex, non-concave, and we have these constraints, standard calculus tools are not going to cut it, are they?
Not at all. Standard differential calculus pretty much, well, gives up the ghost, as you said. We absolutely need the more powerful, more general tools from what's called variational analysis, non-smooth analysis, basically.
Right. So before we even get to their main assumptions, like this KL condition, we need to get the language right, the notation they use.
Absolutely crucial. Let's nail down the basics first. They define standard domain sets, 6 intervals. These are just the domains where px and 4y are finite, respectively. They assume these are closed and convex.
Simple enough. Then there's the set dollar.
Right. Set dollars is where the real action for you happens. Dipple dollars is the intersection of the basic domain dollars and the feasible region defined by the constraints. So dipple dollars y cap, it's the set of allowable values.
And they also define some constants related to these sets, d will I and cool. What are those for?
These are technical constants needed for any complexity proof. They basically ensure the problem is well behaved enough to analyze. Dig A is the diameter of the set dollars.
So the maximum possible distance between any 2 points in dollars.
Exactly. They assume dollars is compact, meaning it's closed and bounded, so this diameter whales is finite. Mac-tol is the maximum variation of the function to dollars over this set dollars. Again, it bounds how much dollar can change.
If these sets were unbounded or the functions could vary infinitely, you couldn't get complexity guarantees, right?
Precisely. You need these bounds to make the analysis tractable. They're standard assumptions in optimization theory when you want convergence rates.
Okay, domains and bounds set. Now for the really key functional definitions. This is where they start formally transforming the minimax problem into something that looks more like a minimization problem. They introduce malloc x, y, y.
Phi x y. Think of this as the objective function for the inner maximization problem, but with the constraint cleverly built in. It's defined as mfy sy pro q y. Your y.
Okay, 3xy is the original inner objective. What's that last term? Phi dollar.
That's the indicator function for the feasible set dollars. It's a standard tool in convex analysis. It's defined to be 0 if Jeff satisfies the constraints. So if you violate...
And if you violates the constraints, if YJSY for some dollar...
then the indicator function dollars is positive infinity.
Ah, I see. So if you try to maximize 5xy and Y steps outside the feasible region, the 5(1)x, the objective function instantly plummets to minus infinity because you're subtracting infinity.
Exactly. It mathematically enforces the constraint. The maximizer dollar will always be forced to stay within the feasible set dollars. It's a neat way to embed the constraint directly into the function we're maximizing.
Okay, that's 5y. From there, they define two even more crucial objects, 5x and del.
Yes. 5x is called the maximal function. It's simply the result of solving the inner maximization problem for a fixed value of 7x.
Yes.
It gives you the optimal value of the inner problem as a function of the outer variable 6y.
And then
It is the overall objective function for the original minimax problem, expressed purely in terms of 6y. It's defined as px plus px. Remember, px was part of the original objective too.
So the original problem plus px is exactly equivalent to just minimizing the single function over 6.
Precisely. That structural equivalence is the critical first conceptual step. They've turned a minimax problem into a minimization problem.
There's a catch, isn't there? This function must be pretty complicated itself.
Oh, absolutely. Because px is defined as a maximum, the maxi(xy), and because the inner function phi was non-concave and mel, these generally non-smooth.
Yeah.
Even if vxex were smooth, taking that maximum often introduces kinks or corners into px.
Which means fx plus px is also likely non-smooth. And that's why standard calculus, gradients, Hessians, they just don't apply directly to
Exactly. This is where we had to bring in the heavy machinery.
Right.
We need tools that can handle non-smoothness.
Okay, so standard smoothness, like Lipschitz continuity of the gradient, is assumed for the base function f tact y f pois way, but they need something more general for tick, right? You mentioned Holder smoothness earlier.
Yes. While Foner's might be lineable smooth, Lipschitz smooth, the resulting maximal function fix and therefore sub-6 might only satisfy a weaker condition called Holder smoothness.
How does that differ?
Instead of the gradient difference being bounded by letter times y1, it's bounded by letter times 1, where the exponent is somewhere between 0 and 1.
So, $20, we get back standard Lipschitz smoothness.
Correct. But if one atoning the gradient is allowed to change more rapidly as points get very close, it's still continuous, but not as uniformly smooth as Lipschitz. This generalization is often necessary because the max operation in Tupic can sharpen things up, locally speaking.
Okay, so Holder smoothness is the target property for Lipschitz. But how do we even talk about gradients when a Tupic might have kinks? This must lead us to subdifferentials.
Directly. When a function isn't differentiable at a point, instead of a single gradient vector, we have a set of possible generalized gradients called the subdifferential.
Right. For convex functions, the subgradient is pretty standard, but here, set isn't necessarily convex because $5 comes from a non-convex, non-concave dollars.
Exactly. So we need more sophisticated notions. The paper uses the limiting subdifferential, denoted partial fit. This is a cornerstone of modern variational analysis for non-convex, non-smooth functions.
How is it defined, roughly? Is it different from the regular subdifferential Fetcher?
Yes, it is. The regular subdifferential Fetcher is defined using a limit infimum of difference quotients, kind of like the definition of a derivative. But for non-convex functions, this Cefic can sometimes be empty, which isn't very helpful.
Okay, so the limiting subdifferential fixes that.
It does. The limiting subdifferential partial fake at a point $6 is defined by considering sequences of points Tickwick that converge to 6s and sequences of regular subgradients partial in Hicks nearby points. The limiting subdifferential partial fake is the set of all possible limit points of such sequences, FCAX.
Okay, so it's like looking at the slopes, the regular subgradients, at all the points nearby $6 and seeing where those slopes tend towards as the points get infinitely close to $6.
That's a very good way to think about it. It captures the limiting geometric behavior of the function's slopes around $6, even if the function is nasty as $6 itself.
And what does this buy us? Why is this limiting construction so powerful?
It has much better mathematical properties. For the functions we care about, like sectional fangs, the limiting subdifferential partial phi is guaranteed to be a non-empty closed set. And for locally Lipschitz functions, it's also convex. This gives us a robust object to work with.
And critically, it lets us define a notion of stationarity, right? Like a 0.6 is a stationary if T others is in the limiting subdifferential partial.
It's exactly. $0 in partial phi becomes the generalized first-order necessary condition for optimality, replacing Nobel-Zollars from smooth optimization. Without the limiting subdifferential, you couldn't even properly state the target condition for an optimization algorithm in this non-smooth, non-convex setting.
Okay, so partial phi is the essential algebraic tool for handling the non-smoothness. Now, you also mentioned a geometric tool, the limiting slope, denoted nobla phi. How does that connect?
The limiting slope is intuitively a measure of how steep the function C-viles near $6, taking into account its potentially non-smooth nature. It's defined formally using the regular subdifferential, but the key insight comes from its connection to the limiting subdifferential.
And what is that connection?
The paper highlights this in Lemma 4a, drawing on standard results. For the class of functions they consider, the limiting slope files is precisely equal to the distance from the origin 0 vector to the limiting subdifferential set partial phi. So mala phi partial.
Whoa, okay. So the geometric steepness measure is equal to the distance from 0 to the set of generalized gradients.
Yes, and think about what that means. If the function is smooth at 6,1, partial phi just contains the single vector cola fixophine, and partial phi is just the norm of the gradient.
Which is our usual measure of steepness or distance from stationarity.
Exactly. If the function is convex, Text-Nestel-Fisher measures how far the set of subgradients is from containing the origin, which would mean sex is a minimizer.
And now they're saying, even for our complicated, potentially non-convex, non-smooth partial phis, serves as the unified measure of first-order stationarity. The smaller this distance, the closer we are to a stationary point.
Precisely. This is a fundamental insight. They've managed to translate the complex, non-standard geometry of the problem into a single, non-negative scalar value limiting slope. Or equivalently, the distance to the subdifferential, which is exactly what you need if you want to measure progress and prove convergence rates for an algorithm. It's the metric the algorithm will try to drive towards 0.
Okay, that clarifies the essential tools, limiting subdifferential and limiting slope. Now we can finally talk about the assumption that powers the whole analysis.
Yes, we arrive at the geometric core. The local Kurdyka-Ło KL condition, this is assumption 1 for Oliver, and it really is the engine driving their results.
But crucially, they don't just assume the original inner function $x satisfies this KL condition, do they?
No, and this is a really clever move. They impose the KL condition on a novel lifted minimax problem. This is formulation 14 in the paper. It involves not just $6, but a new auxiliary variable. Let's call it 6.
Okay, hold on. Why the need for this lifting? Why introduce a third variable $? What does that accomplish?
The variable C is introduced specifically to help handle the difficult inner constraint. It allows them to define a special surrogate constraint, C, which plays a vital role in the inner optimization algorithm. Algorithm 1, the SCP method.
Ah, okay. Let's look at this surrogate constraint.
Yeah.
It's defined in equation 11. For each original constraint, Cj is Z, they define a surrogate ZZZ.
Right, and look at its form. CZZ, CJZ, plus CJZ, ZZZ, plus Frangé wrangle, plus CJJZC.
Okay, so it looks like a quadratic approximation of the original constraint, CJZ, centered around the point Z. It uses the value CJZ, the gradient nabla CJZ, and this quadratic term involving Z deal.
ZJZ is the Lipschitz constant for the gradient of CJZ. So they assume each constraint function Cj is smooth with a known Lipschitz constant for its gradient.
And what's the significance of this specific quadratic form?
This is beautiful. Because $J is smooth, this particular quadratic construction is guaranteed by standard results, like the descent lemma, to be an overestimate of the original function. An overestimate. You mean J for any jailer?
Exactly. For every jailer, the surrogate constraint function is always greater than or equal to the true constraint function.
Why is that property being an overestimate so important?
Think about the inner optimization algorithm. It's going to work with this simpler surrogate constraint, Sergey dollar. If the algorithm finds a point that satisfies the surrogate constraint, meaning Sergey z for all hour, then because that point two must also satisfy the original constraint, Sergey dollars.
Ah, I see. So working with the surrogate constraint guarantees that any solution you find for the inner subproblem is automatically feasible for the original constrained problem. Precisely. The overestimate property ensures the algorithm doesn't accidentally wander outside the true feasible regions, the dollars. It keeps the iterate safe with respect to the original constraints, even though it's optimizing using the surrogate. That's the structural genius of introducing Zillers and similar.
Okay, so they define lifted function, phi x, the yielder, that uses this surrogate constraint, Seller's boys, and then lemma 3 shows the critical equivalence.
Yes, lemma 3 confirms that maximizing the original inner function z over y's, sing yz, gives the same result as maximizing the lifted function phi xyz over both Yeller's y and 6.
Which means they can analyze the geometry of this potentially nicer lifted problem, nicer because of the surrogate constraint structure, and know that the results apply directly back to the original problem's maximal function 5x.
Exactly. So now let's look at the KL condition itself, applied to this lifted function 15. It's stated in equation 15, it looks a bit intimidating, detal, fate, satal yz,
Right.
text yz, but this inequality only needs to hold for thelo z within a specific set.
Okay, let's break that down piece by piece, conceptually. What is the KL condition really saying?
Think of it as a quantifiable guarantee about the steepness of the function landscape near an optimal point. The left side, fetal x, y, z, and a z, that's the optimality gap for the inner lifted problem. It's how much function value you're missing by being at delo z instead of at the true maximum peak for the fixed bar.
Okay, the gap to optimality. Raised to the power of
And the right side, texel y, z, that's the limiting slope we just discussed. It's the measure of how far the generalized gradient with respect to delo z is from 0. It measures how non-stationary the point mile z is for the inner problem.
So the inequality is relating the optimality gap to the stationarity measure.
Exactly. It says that the distance to stationarity, the slope, must be lower bounded by some constant times the optimality gap raised to the power to theta. In simpler terms, if you're still far from the optimal value, large gap, the function must be sufficiently steep, large slope, in a way quantified by Laird or dollars. The function can't become too flat prematurely before reaching the optimum.
It guarantees a certain amount of push towards the optimum related to how far away you are.
That's a great way to put it. And the exponent theta, which is between 12,2 and a 2, dictates how strong that push is.
Okay, but you said this only has to hold on a specific set. What's that about? This is the local part of the local KL condition.
Precisely. This is absolutely critical. The inequality doesn't have to hold everywhere. It only needs to hold for pairs that are in the set defined by equation 16.
And how is defined vent?
By it contains points that are first reasonably close to the optimal set for the inner problem within some radius gamma dollars a and d second, where the optimality gap SYZ is itself relatively small. How small? It needs to be less than or equal to sigma times a measure of stationarity for the outer problem.
Wait, the condition on the inner variables z depends on the stationarity of the outer variable sigma. How does that work?
Yes, specifically the gap XYZ must be less than or equal to a constant sigma times partial c plus max z. Here, textile z plus px is the objective for the lifted outer problem, which is equal to our original.
So textile z is the limiting slope of the overall objective function we want to minimize.
Right, and this link via sigma dolls is fascinating. Think about what it implies. When 6 dollars is far from being a stationary point for the main problem, 6 dolls will be large. This means the upper bound on the gap in the definition of sigmometers is large. So sigmometer is a large set. Making the KL condition easier to satisfy it only needs to hold reasonably close to the optimum for sigma nos.
Okay.
But as the outer algorithm progresses and sigmometers gets closer to a stationary point for sigma doll, the term partial ziver will shrink towards 0. This means the upper bound defining vals also shrinks. The seconds become smaller and smaller, containing only points EZL that are extremely close to the inner optimum.
So the KL condition becomes more restrictive, demanding that the steepness guarantee holds even very, very close to the inner maximum, precisely when the outer algorithm is trying to converge accurately.
Exactly. The locality defined by locks adapts based on the progress of the outer optimization. The constant sigma JAWS essentially captures how quickly this local region where the KL geometry must hold collapses as 6-ball approaches stationarity.
That's quite subtle. And the exponent theta in 12 one-oddles, we touched on this, but what's the significance of it being near $12 versus near $1?
A value of theta equals 12.2 is special. This corresponds to what's known as the Kurdyka-Ło PL condition. It's a condition that implies strong convexity in some sense, but is actually weaker. If theta equals 12.2, the KL inequality says the square root of the gap is related to the slope, which leads to very fast, essentially geometric or linear, convergence rates for algorithms.
The easy case, relatively speaking.
Relatively, yes. But the KL framework allows theta to be larger, anywhere in $12. If theta gets closer to 1, the condition of theta becomes weaker. The exponent on the gap is closer to 1, meaning the required slope, the push towards optimum, can be much smaller relative to the gap.
So problems where the best possible theta is close to 1 are intrinsically harder. The landscape near the optimum is flatter.
Much harder, exactly. The convergence rates will be significantly slower, typically polynomial instead of linear. The value of theta fundamentally characterizes the difficulty of the local geometry.
Okay, so we have this powerful, adaptive, local geometric assumption. What are the direct consequences? How does assuming this local KL on the lifted problem help us analyze the original problem, Minx?
It has two major theoretical consequences presented as theorems 1 and 2. These are the bridges back to the properties of the original maximal function and the overall objective.
Let's take theorem 1 first. It connects the KL condition to the smoothness of fit room.
Right. Theorem 1 says that if the lifted inner problem satisfies the local KL condition, assumption 1.4, then the original maximal function has two crucial properties, at least locally around points where it's close to stationary. First, it's differentiable.
Which is not obvious since it's a max function.
Not obvious at all, and its gradient is what you might intuitively expect. Nabla fx, nablax fx, where the unique maximizer of the inner problem, uniqueness is also guaranteed locally by KL. Second, and more importantly for algorithms, nablax satisfies a local holder smoothness property.
Ah, the holder smoothness we discussed earlier. Equation 18 gives the specific bound.
Yes, it shows nabla fx is bounded by a term involving the standard Lipschitz constant of Fabel plus another term that depends explicitly on the KL parameters and a theta and involves tamis raised to the power 1 of theta.
Okay, let's focus on that exponent. This directly links the smoothness of the outer function dollar to the KL geometry of the inner problem.
Absolutely. Look at the relationship. If theta 12.2, the PL-like case, then level x becomes locally Lipschitz smooth, the standard notion.
The easy case leads to standard smoothness.
But if the ad is close to 1, say theta to 1.9.9, then lum 0.9, then 0.1.1, 0.9 to calcium 89, the exponent becomes very small.
Meaning fxa is only barely holder smooth, much less smooth than Lipschitz.
Exactly. It means the gradient nabla fxa can change very rapidly, even for small changes in 60. This tells the outer optimization algorithm, like algorithm 2, that it needs to be much more careful, likely taking much smaller steps, when the inner problem has bad geometry, theta close to 1. The inner geometry dictates the allowable behavior of the outer algorithm.
That's a really clear connection. What about the second consequence, theorem 2? This one is about a local growth property.
Yes. Theorem 2 also follows from the local KL assumption. It provides a lower bound on the optimality gap for the inner problem. fxx by hexes. It says this gap is bounded below by a constant times the distance from Yarrow to the set of true maximizers raised to a power related to the theta.
The power is $1 in equation 20, so if fx takes fx, yx, why does this tell us practically?
It tells us that if we manage to find an approximate solution, UA is considered the inner problem, such that the gap xy is small, then this gap must be geometrically close to the actual set of maximizers. The rate at which you must approach as the gap shrinks is determined by 1/118th it.
If theta is close to 12, the exponent $1 art is close to 2. If theta is close to 1, the exponent blows up towards infinity.
Right. A larger exponent means the objective function grows more slowly as you move away from the optimal set. But the crucial point is that the KL condition guarantees some quantifiable rate of growth. This is fundamental for proving that the approximate solutions found by the inner algorithm, algorithm 1, are good enough to make progress in the outer algorithm.
How do they prove this growth condition? The paper mentions lemma 5.
The idea, sketched from lemma 5, involves analyzing the function s-core, s-square, s-no, derived from the lifted problem. They relate the slope of this function problem, using the limiting slope definition, back to the KL inequality, 15. This allows them to establish an error-bound relationship, which translates into this growth property relating the objective gap to the distance to the optimal set.
It essentially converts the KL condition, which bounds slope by the gap, into a condition that bounds the gap by the distance to the optimum.
Precisely. It provides a robust guarantee that points with small objective gaps are geometrically close to the solution set, with the rate dictated by the KL geometry theta.
Before moving to the algorithms, example 1 in the paper seems important here. It shows why the local aspect of the KL condition is essential.
Yes, that's a great illustration. They construct a simple 1D function, theta at 7y, where a global KL condition would fail. At certain points, $6, the inner function, fill in dot and y-wire, the optimizer's jaw, where the subdifferential partially fy contains 0, so the slope distance is 0, but the optimality gap, fill x, is still positive for nearby years.
So the KL inequality scale, like Lexixel, would fail because the right side is 0, but the left side is positive.
Exactly. If you demanded the KL property to hold globally for all years, the theory would break down for this example function.
But their local KL condition can still hold.
Potentially, yes, because the local KL condition only needs to hold on the set late cap, which shrinks as $6 gets closer to stationary. It might be that the problematic points where slope is 0 but gap isn't fall outside the shrinking set when $6 is close enough to the solution.
So the local restriction cleverly sidesteps these pathological points by only requiring the geometric guarantee where it's actually needed for the algorithm's convergence analysis.
That's the key insight. The local nature, tied to the outer problem's progress via sigma, is mathematically necessary and sufficient for their proofs to work, even for functions that lack nice global geometric properties. It's a very elegant way to handle the potential complexities of the non-convex, non-concave landscape.
Okay, the theoretical foundation based on the local KL condition is now much clearer. Let's see how they operationalize this. Section 3, solving the inner problem. They need an algorithm to actually find an approximate maximizer G taller for a given $6.
Right, and remember, the inner problem maxi fxy is equivalent to ini. So let's call this objective t plus key, where G plays is generally non-convex, key y is convex, and we have the constraint Li t. This is still a hard, constrained, non-convex minimization problem.
So how do they tackle it? They propose algorithm 1, a sequential convex programming SCP method. What's the core idea of SCP?
SCP methods work by iteratively solving a sequence of simpler, typically convex subproblems that approximate the original difficult problem.
Okay, so what's the subproblem they solve at each iteration, 7tel, or tela, okay, using their double index notation, inside algorithm 1? It's given in 27.
At each step, starting from points k, they want to find the next point cl plus 1 at. They do this by minimizing an approximation of the objective z subject to an approximation of the constraints.
How do they approximate the non-convex part des dl des sel?
They build a convex quadratic model around the current point ck. The model includes the linear term based on the gradient OGK, which is now SEK, plus a quadratic proximal term, Chaklar. They also add the original simple convex function, GCAS.
So the objective in the subproblem 27 is Langle-Nabla GCK CZK plus Frackenauer plus QS. Is this convex?
Yes. Since Q's is convex and the first two terms form a strongly convex quadratic function, provided Langle is positive, the overall objective function for the subproblem is strongly convex.
Okay, that's good. Minimizing convex functions is much easier. What about the constraints? They don't use the original C's in the subproblem, do they?
No, this is where the lifting and the surrogate constraint come into play. The subproblem, 27, minimizes the convex quadratic model subject to the surrogate constraint CGZD2.
Ah, the surrogate constraint plus surge, CGSK plus frac plus ZG2.
Exactly. This surrogate constraint defines a feasible region that is essentially an intersection of balls, or ellipsoids if Segway varies. So the subproblem becomes, minimize a strongly convex quadratic function subject to convex quadratic constraints, the CLD part, and potentially the simple convex constraint from Cuzy's domain. This is a tractable convex optimization problem.
Okay, so SCP iteratively solves these convex approximations, but how do they guarantee that solving these approximations actually makes progress on the original non-convex problem over z-gators? This seems like the crucial step.
This is where the backtracking line search comes in, specifically the condition in line 5 of algorithm 1. After solving the subproblem to get a candidate point zk plus 1, they check if this point yields sufficient decrease in the original objective function $.
The condition is beta plus 1 NASK plus 1i. Let's unpack that.
NASK plus 1i is the actual value of the original, potentially non-convex, objective at the new point. Eta zk is the value at the current point. The term beta ck plus 1 represents a required amount of decrease proportional to the square of the step length. Beta z is a positive constant.
So the algorithm only accepts the step zk plus 1i if the actual decrease in the true objective dollars is significant enough relative to how far it moved.
Exactly. It prevents the algorithm from taking tiny steps that yield almost no improvement, or steps that might even increase the objective, which could happen if the convex model was a poor approximation. If the condition isn't met, the algorithm increases the coefficient $, in the subproblem, making the quadratic term stronger, effectively shrinking the step size, and resolves the subproblem.
So it adapts algorithm until a resulting step is good enough according to this sufficient decrease criterion.
Precisely. This sufficient decrease condition is the linchpin. It's an algebraic condition that ensures meaningful progress is being made on the original non-convex objective at each iteration. And it's this condition, when combined with the geometric KL assumption, that will allow them to prove convergence.
Okay, let's dive into that proof structure. Section 3.2 gives the rigorous analysis. Theorem 4.2 starts with the KKT conditions for the subproblem solution zk plus $1.
Right. Since the subproblem 27 is the convex optimization problem, its solution zk plus 1, they drop the algorithmic chucks once the line search succeeds, must satisfy the Karush-Kuhn-Tucker KKT necessary and sufficient conditions. Condition 31 is the stationarity condition.
It says $0 in nabla plus LKCK plus 1CK plus partial Q plus 1 plus sing J1 meter plus sum J1 meter plus 1. Blah, that looks complicated.
It is, but break it down. Nabla GCK plus LKCK plus 1CK is the gradient of the quadratic approximation part. Partial QCK plus 1 is the subdifferential of the simple convex part, $2. And the last term, sum lambda nabla, is the contribution from the active surrogate constraints weighted by the Lagrange multipliers, lambda.
Ah, the Lagrange multipliers lambda. These essentially measure the sensitivity of the subproblem's solution to changes in the surrogate constraints.
Exactly. And Theorem 4.2 also includes the complementary slackness conditions, 30, which say that lambda can only be positive if the corresponding surrogate constraint ck plus 1 ck is actually active, equal to 0.
Now, for the overall complexity analysis to work, they need these Lagrange multipliers lambda to be bounded, right? If they could grow infinitely large, the algorithm might become unstable or very slow.
Absolutely critical. If the multipliers blew up, it would mean the constraints were becoming infinitely important, which would wreck any convergence guarantee. Lemma 1 provides exactly this crucial bound.
And how do they get this bound? What assumption is needed?
This relies fundamentally on a standard geometric regularity condition on the original constraints. They assume that the Mangasarian-Fromovitz constraint qualification, MFCQ, holds. This is assumption 2.
MFCQ. What does that mean intuitively?
MFCQ essentially guarantees that the constraint boundaries are well-behaved.
Yeah.
At any feasible point, it requires the existence of a direction dollars, such that if you move slightly in that direction, plus epsilon d, you move strictly into the interior of all the active constraints at again.
So it rules out situations like a cusp pointing outwards, where you're trapped at the boundary with no way to move inwards along all active constraints simultaneously, or redundant constraints that make the gradients linearly dependent.
Exactly. It prevents those kinds of pathological geometries. It ensures the feasible region is regular enough.
And how does assuming MFCQ on the original constraints pace help bound the multipliers lambda associated with the surrogate constraints?
There's a key intermediate result, Theorem 3. It shows that if MFCQ holds for the original constraints, those are the latter, then for any point ck, the surrogate constraint satisfies a property that guarantees the existence of a point providing a strict decrease relative to the constraint value 2k. This guarantee comes with a constant zeta dollars.
So MSCQ on suitor ensures the surrogate dollar is also well-behaved in a quantifiable way, captured by zeta.
Precisely. And this constant zeta from Theorem 3 is then used directly in the proof of Lemma 1 to establish the bound on the L1 norm of the Lagrange multipliers, lambda 1 roundacular.
And the bound dollar is given explicitly, g dy plus bar dy 22 plus mqq. Let's see. It depends inversely on zeta, so better geometry from MFCQ means a smaller bound to dollars.
Right, and it depends positively on d to dollars, bound on gradient of d dollar, d double I to the domain, upper bound on the step size parameter amq, and variation of a dollars. These are all fixed constants related to the problem's definition.
So, Lemma 1 is a major achievement. It proves that the computational difficulty introduced by the constraints, as measured by the Lagrange multipliers, remains uniformly bounded throughout the execution of the SCP algorithm. The bound dollar is fixed.
Exactly. This is absolutely essential for proving finite termination and getting an overall complexity bound later.
Okay, the multipliers are bounded. Now, how does the algorithm's output zk plus $1 relate back to the KL condition we discussed earlier? That connection needs to be made.
That's the job of lemma 8. This lemma connects the step taken by the SCP algorithm, ck plus 1 is k, to the stationarity measure used in the KL condition.
Remember, the KL condition involved text to cell a dollar plus 1 cell. Lemma 8 seems to relate to text to zeller partial cell plus 1 cell, where a cell is the objective part of the lifted problem.
Right.
Cellless. Lemma 8 shows that this distance to the subdifferential at the new point, zk plus 1 ck, is bounded by the step size. Text to zeller partial self-cell plus 1 ck plus 1 celler plus 1 cell. So, the stationarity measure is controlled linearly by the size of the step taken. The constant omega captures the proportionality.
Yes, and the derivation of omega given in equation 33 carefully combines all the relevant constants. The smoothness constants, lemma Lorentzi, the bound dollars, the Lagrange multipliers, and the step parameter, Lobel-Lars.
Okay, so we have two key ingredients now for the SCP convergence. One, the sufficient decrease condition, line 5, beta z plus 1 plus 1 to cry, lemma 8. So lemma 8 is partial 6, 1 plus 1 to z. Lemma 8. How do these combine with the KL condition to give convergence?
This is where the magic of the KL property comes in. The KL inequality, applied to x, relates the optimality gap to the distance text. Lemma 8 gives us a bound on this distance in terms of the step size. The sufficient decrease condition gives us a bound on the step size in terms of the decrease in $. Putting these together allows them to show that the objective value, deco, must converge to the optimal value.
And more than just convergence, they get a rate of convergence and finite termination.
Yes, this is Theorem 5 and the subsequent Lemma 9. By carefully combining the sufficient decrease, the result of Lemma 8, and the KL inequality 15, they can show that the sum of squared step sizes sum dk plus 1 ck must be finite. This implies zk converges to a stationary point.
And the rate depends on the KL exponent beta.
Critically, yes.
Yes.
If the DINA 12-2, the PL-like case, they show that the sequence converges to 0 geometrically, linearly, like 1 plus alpha kiss for some alpha.
Right.
If the theta in 12, the harder, non-PL case, the convergence is slower, only polynomially fast. The decay rate is like theta 1.
So faster convergence for theta 12-2, slower but still guaranteed convergence for theta 12-2. And because it converges, it must reach any desired accuracy T on a finite number of iterations.
It's exactly. Theorem 5 formally states that algorithm 1 terminates in a finite number of iterations. Let's call it theta. And crucially, the bound on theta depends explicitly on the initial gap other end x, the desired accuracy, and the KL parameters theta p of theta.
So algorithm 1 is now effectively a provably finite subroutine. You give it the current outer variables and a target accuracy tau at the inner problem, and it guarantees to return an approximate maximizer EAT, or minimizer C towers for tau, that satisfies the accuracy requirement within a calculable number of steps. The cost of theta depends on the geometry.
That's the perfect summary. SCP becomes a reliable black box for the outer loop.
Excellent. So that brings us finally to section 4, the outer loop. We have this reliable inner solver, algorithm 1. Now we need to use it within an outer algorithm to solve the main problem, minimize fx plus pha.
Right. And since statistics involves a maximal function phi-co, which is generally non-smooth, though locally Holder smooth thanks to Theorem 1, they use a method suitable for such functions. An inexact proximal gradient
IPG method. This is algorithm 2.
Why inexact?
Because we can't actually compute the true gradient nabla FSK easily. Remember nabla FXK, where $, is the exact inner maximizer. We don't have YK. We only have the approximate maximizer curve computed by algorithm 1, the SCP method.
So the inexactness comes from using the approximate gradient MXK YK as a stand-in for the true gradient ABLF XK.
Precisely. The core challenge is to show that this approximation is good enough to still guarantee convergence.
Okay, let's look at the main step of algorithm 2, the update for 6K plus 1. It's in line 4. It looks like a proximal step. FSK plus 1 Laplace, FXK YK, RBR, SK wrangle plus PXK Ry. Let's break this down.
Okay, first, the objective function being minimized. It includes the linear approximation using the inexact gradient, SK, XA2. It includes the quadratic proximal term, Farquhar 6 LDS, which penalizes large steps. And it includes the original simple convex function, PS.
So it's balancing moving in the approximate negative gradient direction with staying close to the current point, 6K, while also respecting the structure of FARK. What about the step size parameter?
This is important. PS is adaptive, calculated in line 3. Look at its definition, C1 theta, C1 XK theta 1. It depends on the Lipschitz constant of phi 1, and crucially, it depends on the Holder exponent theta that we got from theorem 1.
So the step size calculation explicitly uses the knowledge about the Holder smoothness of Fourier theta, which in turn came from the inner problem's KL geometry theta.
Yes. The term C $1 essentially estimates the local Holder constant based on the previous step. This allows the algorithm to automatically adapt its step size var key to the actual local smoothness, or lack thereof, of the objective function. This adaptivity is key for conversions when you only have Holder smoothness instead of Lipschitz smoothness.
Very clever. Now, what about the constraint on the minimization? SexK and BXK, is the next iterate SexK plus $1 forced to stay within a ball of radius around the current iterate 6K?
This constraint, $6 in BSK, is absolutely crucial and ties directly back to the local nature of Theorem 1. Remember, Theorem 1 only guaranteed the differentiability and Holder smoothness of 5i locally in a neighborhood around $0.6 that are sufficiently close to stationarity.
Right.
The algorithm needs to ensure that the iterate $6 stay within a region where these theoretical guarantees actually hold. If 6K plus others were allowed to jump too far, it might land in a region where $5 is not differentiable or doesn't satisfy the assumed Holder smoothness, and the analysis would break down.
So the ball constraint BXK acts as a safeguard, keeping the algorithm confined to the zone of validity for the smoothness properties.
Exactly. And notice how the radius Doral is chosen, 1 gamma epsilon sigma for LF from line 2, although used implicitly in the theorem proofs. It depends explicitly on the final desired accuracy epsilon for the outer problem and on that KL scale parameter and sigma from the definition of the local set.
Sigma controlled how fast the local KL region $ shrinks. So the step radius $, is smaller if sigma is larger, meaning the region shrinks faster, or if the target accuracy epsilon is smaller.
Precisely. The algorithm explicitly limits how far it can step based on how quickly its theoretical guarantees might become invalid as it approaches the solution. It's another layer of careful control needed because of the complex local nature of the problem's geometry.
Okay, so the outer step computes 6K plus $1 using the inexact gradient, adaptive step size law, and the radius constraint in $. Then in line 5, it calls the inner loop solver, algorithm 1 SCP.
Yes, it calls SCP to find the next approximate maximizer YK plus 1 corresponding to the new point sexy plus 1. This GK plus 1 will then be used to compute the inexact gradient Teta Black's FXK plus 1 in the next outer iteration.
Now, a crucial detail here must be the accuracy requirement tau that's passed to the inner SCP solver in line 5. It can't just be any arbitrary small number, can it?
No, absolutely not.
Yeah.
The required accuracy tau for the inner solver is carefully chosen to be tightly coupled to the overall target accuracy epsilon for the outer problem. Lemma 10 makes this precise.
What does Lemma 10 guarantee?
It shows that if the inner SCP algorithm, algorithm 1, is run with a specific stopping criterion tau, which depends on epsilon, theta, and sigma as defined in tau 1, then the output teller will be good enough. Specifically, it guarantees bounds on both the optimality gap for the inner problem, FSK-YK, and the distance of Yasma to the true maximizer set.
And these bounds are small enough relative to epsilon.
Yes. The bounds are controlled in such a way that the error introduced by using the inexact gradient XKOK instead of the true gradient XKYK is small enough that the outer IPG method still converges correctly towards an epsilon accurate solution for Chaos. The choice of tau ensures the inner errors don't accumulate and derail the outer progress.
So the whole scheme is carefully balanced. The outer loop takes cautious steps within a safe radius, using an inexact gradient, but the inexactness is controlled because the inner loop is required to solve its problem to just the right level of precision, dictated by the overall goal epsilon dollar and the problem geometry theta sigma.
That's a perfect encapsulation. It's a multi-level balancing act, all orchestrated based on the properties derived from the local KL assumption.
All right, let's get to the payoff then. The overall complexity results. How many operations does this whole scheme take? Theorems 6 and 7 provide the answers.
Theorem 6 gives the iteration complexity of the outer loop, algorithm 2. It bounds the number of outer iterations, let's call it cupsilon, needed to find an epsilon stationary point of that. This is a point satisfying the condition in definition 1, which involves the proximal gradient mapping being small.
And what is the bound on expontilon?
The bound is roughly left epsilon max frexma theta, potentially multiplied by some logarithmic factors.
Okay, let's stare at that exponent, fraxigma theta. This looks really important.
It's fundamental. It reveals the two potential bottlenecks that determine the algorithm's speed, stemming directly from the local KL conditions parameters.
The first term, 1L1 theta, relates to the KL exponent theta. If theta is close to $12, this term is close to $2. If theta is close to $1, this term blows up.
Right. This term represents the cost associated with the intrinsic sharpness or geometry of the objective function near the optimum. Flatter landscapes, now 1 on theta, require exponentially more iterations.
The second term, sigma theta, involves the scale parameter sigma from the definition of the local set, Dave dollar. What does this term represent?
This term represents the cost associated with the scale of the problem, or how quickly the region, where the KL condition holds, shrinks as we approach the solution. If sigma is large, the region shrinks quickly. The radius dollars needs to be smaller, and the algorithm might need more iterations to cover the distance while staying within the valid zone.
So the total number of outer iterations, epsilon, epsilon, is dominated by whichever of these two factors imposes a stricter requirement. The intrinsic geometry cost, $1 theta, or the local scale cost, exim theta.
Exactly. The algorithm's outer loop complexity is dictated by the worst of these two challenges presented by the problem's specific KL parameters.
Okay, that's the number of outer iterations, but each outer iteration involves calling the inner SCP solver, algorithm 1, which itself takes multiple steps. What's the total work? This must be theorem 7.
Yes. Theorem 7 gives the total first-order oracle, FO, complexity. This counts the total number of gradient evaluations of 5-place node performed across all iterations of both algorithms, which is usually considered the dominant computational cost. Let's call this total cost, nipsilon.
And how does epsilon depend on tepsilon and sigma?
It depends heavily on theta. The paper analyzes two cases. Case 1, 4 theta, 12-2 PL-like condition. In this relatively easier case, the total complexity is 1 PL1. It's polynomial in $1 epsilon, with the exponent determined mainly by sigma.
Manageable, it seems. Polynomial complexity is usually considered good for non-convex problems.
Right. But now look at the harder case, case 2, theta in 12, truly non-PL. Here, the complexity becomes significantly worse. The exponent on $1 involves a complex combination of theta and sigma. It's roughly epsilon left, frexilon left, plus frexilon lever, 4 thites again, possibly with log factors.
Whoa, that exponent looks nasty. The term fracto 2 theta plus 1 theta blows up as theta to the Matner, and it multiplies the Maxter term we saw in the outer iteration count.
Exactly. The total work depends very sensitively on how close the theta is to 1 frac. The fact that the theta appears in the exponent and in such a complex fractional form really highlights the steep computational price paid for solving problems where the local geometry is weak, i.e. lacks the PL property.
But the crucial point remains. Despite the potentially high exponent, they have derived an explicit complexity bound.
Yes, that's the main achievement. They took this class of extremely challenging problems, constrained, non-convex, non-concave minimax problems, which often only had empirical results or analyses under much stronger assumptions, like global concavity and fatter, and they provided the first complete algorithmic framework with rigorous, quantifiable FO complexity guarantees.
And these guarantees are expressed directly in terms of the problem's intrinsic geometric properties, captured by the local KL parameters theta and sigma.
Precisely. They've successfully connected the algorithmic performance back to the fundamental geometry of the solution landscape via the KL condition and the lifted formulation. It's a
very significant theoretical contribution.
Okay, that's a deep dive into the theory and algorithms. To make sure this isn't just castles in the sky, let's briefly touch on the numerical example they provided in Section 5. Did it validate the approach?
It did seem to. They constructed a specific test problem, equation 43, that fits their framework. It had a quadratic term in sextile, a bilinear term, and importantly, a nonconcave term involving d-Alger for the inner variable dollar.
So the inner problem was genuinely non-concave, and the constraints.
They use constraints.
Yes.
A Tauger where pan your dollar involves sums of exponential terms, equation 44. These are smooth but highly nonlinear, designed to test the SCP method's ability to handle challenging constraint boundaries using the surrogate D.
And what were the results when they ran algorithm 2, the IPG outer loop, calling the SCP inner loop?
The results, shown in Table 1, were quite striking. First, the algorithm demonstrably worked in terms of minimizing the objective. For instances, with dimensions up to $1 and to $1.55, the objective value was driven down significantly from initial values around 1.4 to final values like negative 579.
So it found much better solutions than the starting point, confirming the overall optimization capability.
Yes, but perhaps more importantly for validating the theory, they looked at the accuracy of the inner solution capsilon found by SCP. They compared the final objective value, which relies on the true epsilon, capsilon, those dots calculated using the inexact epsilon.
And were they close?
They were extremely close. The difference was on the order of $10 or $10 out. This provides strong numerical evidence that the SCP inner loop, guided by the theoretical accuracy requirement derived from the KL analysis, was indeed finding a high-quality approximate maximizer epsilon.
Which in turn justifies the use of the inexact gradient fx epsilon ubilin in the outer IPG lim. It confirms the whole framework holds together in practice, at least on this example.
Exactly. It suggests the inexactness was properly controlled and didn't prevent the algorithm from reaching a point very close to satisfying the true stationarity conditions.
Okay, so let's try to synthesize this. Liu and Wang tackled constrained non-convex, non-concave minimax problems, a really tough area. Their key contribution seems to be leveraging this local Kurdyka-Ło condition.
Absolutely. By imposing the local KL condition not directly, but on a cleverly designed lifted problem involving the surrogate constraint, they unlocked the whole analysis.
This KL condition then gave them two crucial things. Local Holder smoothness for the outer maximal function, phi effects theorem 1, and a local growth condition for the inner function, theorem 2.
Right. The Holder smoothness allowed them to analyze an inexact proximal gradient method, algorithm 2, for the outer loop, carefully controlling the step size mark and the step radius, $3, based on the KL parameters, beta and sigma.
And the growth condition, combined with the sufficient decrease from the line search, allowed them to prove finite termination, theta steps, for the sequential convex programming inner loop, algorithm 1, used to handle the non-concave constrained inner problem.
And putting it all together, they derived the first explicit first-order oracle complexity bounds, theorem 7, for this problem class, showing how the total work not applied depends directly on the geometric parameters as T theta and sigma, and the target accuracy, epsilon.
It feels like a really complete theoretical package. They didn't just propose an algorithm, they built the entire analytical framework needed to justify it and quantify its performance based on fundamental geometric properties.
I agree. It's a significant step forward because it moves beyond heuristics or assumptions of interconcavity, providing a robust foundation rooted in variational analysis and the KL condition.
Which brings us, as always, to our final provocative thought for you, the listener. We've seen how the entire performance analysis, the adaptive step sizes, the inner loop accuracy, the finite termination nikaida, the overall complexity ninometida, it all hinges critically on knowing these local KL parameters, theta and sigma.
Yes, the theory assumes these constants, which describe the deep geometry of the solution landscape near the optimum, are known in advance.
But in practice, when you're faced with a complex machine learning problem, say training a Jan with weird constraints, you almost certainly don't know the precise values of theta and sigma for your specific problem instance. They depend on the data, the network architecture, everything.
That's the practical gap. The theory provides the guarantee if you know the geometry, but measuring that geometry directly is usually infeasible.
So the provocative question is, what's the next step? If the complexity is so heavily dependent on these unknown geometric constants,
could the next breakthrough be in developing algorithms that are adaptive not just in their step size gable, but adaptive to the geometry itself?
meaning methods that could somehow estimate the local values of the theta and the sigma on the fly as the optimization progresses.
Exactly. Imagine an algorithm that probes the local landscape, perhaps by observing the relationship between objective decrease in step size or stationarity measures, and uses that information to dynamically adjust its parameters, like the inner stopping tolerance tailor or even the outer step strategy, without requiring theta and sigma as explicit inputs.
That sounds like a path towards truly parameter-free, robust methods for these complex minimax problems, if algorithms could learn the relevant geometry as they run.
They could potentially achieve near-optimal performance automatically, regardless of whether the underlying problem has good geometry or the bad geometry, their bad geometry, neither one. It's a very challenging goal, but perhaps the most promising direction for making these theoretical advances truly practical across the board.
A fascinating objective for future research indeed. Something for you to ponder. Thank you for joining us for this deep dive into the mathematics behind constrained, non-convex, non-concave optimization. We'll see you next time on the deep dive. Okay, let's unpack this. We are diving deep, really deep, into a realm of high-stakes mathematical optimization. We're tackling a specific kind of problem that sits right at the core of a lot of advanced machine learning, things like control theory, operations research. It's called constrained, non-convex, non-concave minimax problems.
Right, and it's not just about finding a simple minimum value. It's this adversarial setup, you know?
Yeah.
You're trying to find an optimal strategy, let's call it X, that minimizes some quantity. But that quantity itself is the result of an opponent trying to maximize their outcome.
And all of this is happening under potentially really complex constraints. It's like a game with rules.
Exactly, a very complicated game.
So our mission today, for you listening, is pretty specialized. We want you to get a fast but really thorough understanding of the newest first-order methods that have been developed for these exact constrained problems. We're going to focus intently on the rigorous math side of things, the formal setup, the specific notation you absolutely need to analyze these kinds of non-smooth, non-convex systems. And, crucially, the logic behind the derivations, the steps that actually guarantee these methods converge.
Well,
we're digging into the fundamental theory.
Yeah, what's really fascinating here, I think, is the core technical challenge. How do you actually handle the constraints, especially in that inner maximization part? You know, when the functions involved are messy non-convex, non-concave, your standard gradient methods, they break down almost immediately.
Right.
So the authors here, they tackle this difficulty head on using a really powerful but, yeah, pretty technical tool. It's called the local Kurdyka-Ło condition, or KL condition for short.
KL condition, okay.
Our job today is basically to break this paper down. We need to define every key mathematical concept and try not to just read out equations, but explain what they mean. And then connect that theory, specifically how this local KL condition gives rise to a kind of weird, non-standard smoothness property, Holder smoothness, connect that all the way to the hard computational guarantees. How many steps does it actually take?
Makes sense. So our sources are excerpts from this paper, a first-order method for constrained non-convex, non-concave minimax problems under a local Kurdyka-Ło condition. We'll focus really intently on the theoretical foundations first. That's sections 1 and 2. They basically lay down the rules of the game, the mathematical language. Then we'll shift gears and look at the algorithms themselves. Sequential convex programming and the inexact proximal gradient methods. That's sections 3 and 4.
Yeah, it's definitely a journey into modern optimization theory, really connecting the abstract math, the algebra, to actual computational performance.
Okay, let's start right at the heart of it. The specific optimization challenge. The authors define this primary problem they're solving. Equation 1 in the paper.
Exactly. And the structure is min over x, max over y, subject to cy, less than or equal to 0 of this function, fxy plus px minus qy. We really need to pause here and carefully define each piece, the f, the p, the q, and the c, because understanding those is key to seeing where all the difficulty comes from.
All right, starting with f. This is fxy, the main objective function. It's smooth, they assume, which sounds helpful. But the catch is it's possibly non-convex in x, the variable we're minimizing, and it's possibly non-concave in y, the variable being maximized.
Right. That non-standard structure, that push and pull between x and y, is what makes it a minimax problem in the first place. It immediately takes us out of the nice, clean world of simple convex optimization.
The x and y variables are sort of working against each other.
Constantly fighting, yeah. Then you've got the regularization terms, px and qy.
Now, these are specified as simple closed convex functions. And that word simple is actually doing a lot of work here, especially for first-order methods.
What does simple mean technically in this context?
It means their proximal operators can be computed easily, efficiently, like in closed form or with a very fast algorithm.
Okay, the proximal operator. That's that specialized operation you need for proximal gradient methods, right?
Exactly. If P or Q were some horribly complicated convex functions where computing the prox operator was itself a huge task, the whole algorithm we're building towards would just grind to a halt. So simple means computationally tractable.
Got it. And finally, the constraint, CY,
Right.
less than or equal to 0. This is a smooth mapping, C, but it represents potentially complex, maybe nonlinear constraints. And critically, they only act on Y, the inner maximization variable.
And that inner constraint, CY less than or equal to 0, is really the game changer in this paper. It's the main source of difficulty that the authors are trying to get around using this whole KL approach.
How so? What's the challenge it introduces compared to, say, unconstrained problems?
Well, if you look at the existing research, most of the really successful first-order methods, the ones with solid guarantees, they focus on the unconstrained inner maximization case. Like if you just didn't have that C-high constraint at all.
The problem would be much simpler.
Dramatically simpler. You could use other techniques. But this paper tackles the hard case, the constrained inner problem. And that's where traditional methods like basic Lagrangian approaches often struggle because the overall function isn't convex and the constraints interact badly with the maximization.
Okay, but why do we care so much about solving this specific constrained form, equation 1? Is it that common?
It's more foundational than common on its own. The paper immediately points out its connection to even more general problems. Think about equation 2 in their discussion. That's where both x and y have complex constraints. Min over x, where debit x is constrained, max over y, where cy is constrained, of the same f plus pq objective.
Okay, so constraints on both variables.
Right. Now, how do you solve that? A standard approach is to use a penalty method for the outer constraint, the dx part. You add a penalty term, maybe quadratic, to the objective for violating dx, less than or equal to 0.
Okay.
This converts the problem with the outer constraint into a sequence of problems that are unconstrained on the outside. But each subproblem in that sequence looks exactly like equation 1. It has the inner constraint, cy, still there.
I see. So you solve a series of these equation 1 type problems, maybe making the penalty for violating dx stricter each time.
Exactly. And the solutions to that sequence of subproblems will converge to the solution to the original, doubly constrained, more complex problem too.
So being able to efficiently solve equation 1 is like having a fundamental building block. It unlocks solutions to a much wider class of constrained optimization and equilibrium problems.
Precisely. It's a critical subroutine, in a sense. Hashtag tag key notation to definitions,
Yeah.
section 1.1.
All right, let's shift to the language, the mathematical tools we need to actually analyze these structures properly. Because we're dealing with stuff that isn't just smooth and convex, we need some specialized notation, right, to talk about distance and change and directions.
Absolutely. You need the right vocabulary. We start with the basics, of course. Euclidean spaces, standard norms like the L2 norm, denoted translane break, to measure distance. That's straightforward. But the complexity bites almost immediately when you start talking about how the function changes. Things like continuity and gradients. Because, as we'll see, the function we end up optimizing, this fx, it won't be smooth in the standard textbook sense.
Okay, so standard smoothness first. The paper mentions L smoothness, specifically L nabel F smoothness. That means the gradient doesn't change too quickly, right?
Yeah, it's Lipschitz continuity of the gradient. If you move a certain distance, say d, the gradient vector itself shifts by, at most, L times dou.
Yeah.
It's a linear bound on the changing gradient. Very common assumption.
But not enough here.
Not enough here. The critical generalization they need, and which the KL condition will eventually give them, is Holder smoothness.
Holder smoothness. Okay, what's the difference?
It's essential because, spoiler alert, the KL theory is going to imply that this maximal function fx is generally not Lipschitz smooth. Holder smoothness basically weakens that linear relationship.
How?
A function is Holder smooth if the change in its gradient is bounded by the distance between points raised to some power, let's call it nu, where nu is between 0 and 1, typically strictly less than 1 in interesting cases.
So ux young, x uy.
Exactly. If nu equals 1, you just get back standard Lipschitz smoothness, L times distance to the power of 1.
But if nu is, say, 0.5 square root smooth.
Precisely.
then the gradient change is bounded by the square root of the distance xy12. This means the function is still continuous, its gradient is still continuous, but it can change more sharply or be flatter in other places than a Lipschitz smooth function.
And understanding how the KL condition actually derives the specific exponent nu.
That's the mathematical core, yeah. The whole analysis hinges on establishing that specific non-standard smoothness property and figuring out what nu is based on the KL parameters.
Okay, now for the real rigor, subdifferentials. Since our functions p and q are convex but maybe not smooth, and we have constraints, which we often represent with indicator functions, those aren't smooth either.
Right. Gradients are only defined for smooth functions. When a function is convex but has kinks or corners like absolute value, we use the subgradient. It's a set of vectors that define supporting hyperplanes.
But here, f is non-convex, and we have the constraints. So we need something even more general.
We do. We need tools from non-smooth, non-convex analysis. The paper starts with the regular subdifferential, denoted at x. Conceptually, you can think of this as the set of all vectors that act like local uphill directions right at the point x.
How is it defined? It's not just a simple derivative.
No, it's defined using a limit inferior formulation. You look at the directions from points really close to x, and you check if a candidate vector y satisfies a kind of minimal upward slope condition locally. It's quite technical.
But that's not the one we really use for the heavy lifting.
Generally, no. The one that forms the bedrock of the analysis, especially for convergence proofs in non-convex settings, is the limiting subdifferential, denoted x.
Okay, limiting, how does that relate to the regular one?
The limiting subdifferential is essentially a more robust version. You build it by taking limits of regular subgradients from nearby points. So think of it like this. If you have a sequence of points xk converging to x, and you have corresponding regular subgradients vk for xk that converge to some vector v, then that limit vector v belongs to the limiting subdifferential x.
Ah, okay. It's like a stabilization process. Taking the limit makes the set better behaved.
Exactly. The resulting set Rx has crucial properties. It's always a closed set, and it's guaranteed to be non-empty under very broad conditions, which is vital. You need these properties to rigorously prove that algorithms converge to points where this set contains the zero vector. So the limiting subdifferential is our robust, generalized gradient for these messy functions. How do we use it to measure progress? Like, how far are we from a solution point? Good question. We use the concept of slope, specifically the limiting slope written Rx. The slope is intuitively a measure of the function's steepness right around x. The limiting slope stabilizes this measure, similar to the limiting subdifferential.
And there's a key connection.
Absolutely critical connection. It's stated in lemma 4i of the paper. The limiting slope at a point, say u, is exactly equal to the distance from the zero vector to the limiting subdifferential set at that point.
So, precisely. That identity is the linchpin.
Why is that so crucial? Because our goal in optimization is usually to find a stationary point, a point where the gradient is zero. For these non-smooth problems, that means finding a point where the zero vector is in the limiting subdifferential. So the condition dist 0 characterizes optimality, and the value dist is 0, which equals the limiting slope, gives us a quantifiable measure of how non-stationary we are.
Ah. So when we talk later about finding an epsilon stationary point, we mean finding a point x where this distance to 0 is less than epsilon.
Exactly. The limiting slope provides the precise numerical value we need to track for convergence analysis. It connects the geometry of the subdifferential directly to a value we can try to drive down. Hashtag the lifted problem, the author's novel. Okay, we have the notation, the subdifferentials, the slope. Now, before we even get to the KL condition itself, the authors do something structural. They introduce this concept of the lifted problem. Yes, this is a really important maneuver. Before they could apply the KL machinery, they need to structure the problem in a way that's, let's say, compatible with it. They start, naturally, by bundling the inner objective. They define fxy as the original fxy minus qy, but they also include the constraint, cy 0, implicitly.
Well, how implicitly? Using an indicator function.
Exactly. They add minus delta c. The delta is an indicator function. It's 0 if y satisfies the constraints and plus infinity otherwise. So maximizing fxy automatically enforces the constraints.
Makes sense. It builds the constraint into the function itself.
And then fx is just a result of that inner maximization, xx fxy. This fx is the function we ultimately want to minimize with respect to x.
And the overall objective for the outer problem is x fx plus px.
Right. That's the standard way to frame the minimax problem objective. But now comes the author's novelty. the lifted minimax problem.
This involves introducing a new variable z equation 10 in the paper.
Correct. They define a new lifted function, f(x,y), and a new optimization problem.
Wait a minute. The problem is already complicated with x and y. Why add another variable z and seemingly more complex constraints involving z? Isn't that just making the problem higher dimensional, potentially harder to solve? What's the motivation here?
That's the absolute right question to ask. It seems counterintuitive, right?
Yeah.
Adding complexity.
Yeah.
The trade-off is all about mathematical tractability and enabling the KL analysis. They define this lifted function, f, and the lifted problem, EQ10. The key is how the constraints are handled in this lifted space. They introduce a surrogate constraint, G, 0, 0. Look at equation 11. This GAZ isn't the original constraint CJAY. It's a quadratic approximation of CJ, but centered at the new anchor point Z.
Quadratic approximation, so it's using gradient and maybe Hessian info of the original constraint C at the point Z?
Exactly. It's essentially CJZ plus AH AD YZ plus a quadratic term involving YZ2. It's a local model of the constraint near Z.
Okay, so Z acts as an anchor point for a local, smoother approximation of the original constraint set.
You've got it. That's the core insight. This lifting, introducing Z and using C, is the crucial technical step. Why? Because the original constraints, CY as ZO, might be the source of nasty, non-smooth behavior that prevents the KL condition from holding directly for FCO.
The original constraint set might have sharp corners or weird geometry.
Precisely. By using this quadratic surrogate constraint, CA, which is inherently smoother because it's derived from the smooth function C, they create a surrogate feasible region parameterized by Z. This region is locally well behaved.
And this lifted structure, X, Y, Z, with the C constraint is amenable to the KL analysis.
Yes, that's the whole point. It's constructed specifically so that assumption 1, the KL condition, can be reasonably applied to F with respect to Y and Z. It's much harder, maybe impossible, to guarantee KL holds for the original F with the original hard constraints.
But does solving this lifted problem give us the solution to the original one? We haven't changed the actual answer we're looking for, have we?
Excellent point. Lemma 3 in the paper provides the crucial link. It proves rigorously that the optimal value of the original inner problem and the lifted inner problem are identical. That is, fx equals x.
So mathematically equivalent.
Equivalent in terms of the optimal value. We haven't changed the fundamental problem we're solving, only the mathematical framework we're using to analyze it and ultimately to design the algorithm for the inner loop. This lifted framework, with its smooth surrogate constraint, provides the necessary structure for the KL theory to work its magic.
Okay, so we've got the problem set up, we've got the notation, and we have this lifted structure, F. Now we can finally bring in the engine driving the theoretical guarantees, the KL condition.
Exactly. This condition is the rigorous mathematical bridge. It connects how far we are from the optimal value in terms of function difference to how steep the function is in terms of the size of the subgradient.
It's stated as assumption 1 in the paper applied to the lifted function f, specifically with respect to the inner variables y and z. It looks pretty dense mathematically.
It is dense. Let's try to unpack the relationship it formalizes without just reading the symbols. Essentially, the KL condition establishes a controlled relationship. On one side, you have the optimality gap for the inner problem, f, x, y, z. That's how much higher the current function value is compared to the minimum or maximum, depending on context. Here it's related to maximization gap.
Okay, the function value difference.
On the other side, you have a measure of non-stationarity, the distance from the zero vector to the subdifferential of f with respect to y and z. That's disco 0, s, y, z.
Which we know relates to the limiting slope, so steepness.
Right. The KL condition says there's a specific inequality linking these two. It states that the optimality gap raised to the power theta is controlled by, or bounded by, the size of the subgradient times a constant c.
So rearranging, the subgradient size gives a lower bound on the function gap, or the function gap gives an upper bound on the subgradient size, depending on how you write it. The paper writes c times gap subgradient size.
Let's use the form from the paper. C, optimality gap, is subgradient size. This essentially says that if the gap is small, the subgradient can't be too large. Or, more usefully for analysis, it implies that the subgradient size provides a lower bound for the gap. Subgradient size, C, the gap.
Okay, let's look at the parameters controlling this. There's a constant C0, And then there's theta, the KL exponent. This seems critical.
Absolutely critical. Theta is restricted to the range 12, 1. That specific range is vital.
Why that range? What happens at the boundaries?
If after 12, that's the strongest form of the condition, it actually corresponds to another well-known condition in optimization called the Kurdyka-Ło or PL condition.
PL condition, I've heard of that. It guarantees linear convergence for gradient descent, right? Even for some non-convex functions.
Exactly. It's a very powerful condition. So
Yeah.
the 80s-12 is the best case scenario within the KL framework.
What about the other end as A gets closer to 1, say 0.9 or 4.99?
As ASIC approaches 1, the condition becomes progressively weaker. A value close to 1 means the function can become extremely flat near the optimal set, even if the subgradient isn't quite 0.
And flatness is bad for optimization algorithms.
Very bad. If it's too flat, gradient-based methods take tiny steps, and progress becomes incredibly slow. So a larger, closer to 1, signifies a fundamentally harder problem, and it directly leads to worse convergence rates in the complexity analysis later.
Okay, so it quantifies the difficulty in some sense. Now, this KL condition, it doesn't have to hold everywhere. The paper talks about a local level set, LX.
Right, this is another crucial aspect, locality. Assumption 1.4 doesn't need to hold for all possible, YZ. It only needs to hold for YZ that fall within a specific set LX.
And what defines the set LX? It looks complicated, involving parameters gamma and sigma.
It is technical. LX is the set of points YZ where first, they are not already optimal, so the gap x, x, yz is greater than 0, and second, this gap is also bounded above by a term related to the non-stationarity of the outer problem. Specifically, times dist 0. So
Whoa, okay. So the size of this required region, LX, depends on how close the outer variable x is to being stationary for the overall problem. That seems intricate.
it's intricate but incredibly important. This is the aha moment the paper highlights in remark 1.2. Think about what it means. The size of the set X, where the KL condition must hold, depends on dist 0 dist.
Wait.
If our outer variable X is currently far from a solution, then dist 0 is large. If 0, then the upper bound defining LX is large. This means LX is a large set. The KL condition needs to hold over a relatively broad region around the optimum of the inner problem.
Okay.
But as our outer algorithm makes progress and X gets closer and closer to a stationary point for X, what happens to dist 0?
It goes to 0.
It goes to 0. And if it's 0, then that upper bound defining LX also shrinks towards 0. The set LX gets smaller and smaller.
So the region where the KL condition needs to hold becomes vanishingly small as we actually approach a solution.
Precisely. This makes the assumption much weaker and more practical than demanding a KL condition that holds globally, or even in a fixed neighborhood. It only needs to hold in a region whose size adapts based on our progress in the outer loop.
That's clever. It lets you apply this powerful tool even to nasty functions where a global condition would almost certainly fail. Hashtag tag KL versus other conditions and locality.
Yeah, and this locality is really what distinguishes it. As we said, KL generalizes PL, which is the 2.12 case, but often PL is assumed globally. Here, the KL condition is inherently local, and that locality is dynamic, controlled by Ta.
Does the paper show this locality actually makes a difference? Like, are there problems that satisfy this local condition but not a global one?
Yes, they provide example 1 specifically for this. They construct a function, fpo, that demonstrably fails to satisfy a global KL condition. However, it does satisfy their local assumption 1.4, and it even does so with the best possible exponent, f12, and some 0.
So it's not just theoretical hair splitting. Their framework genuinely covers problems that previous analyses based on global conditions couldn't handle with sharp guarantees.
Exactly. It broadens the applicability of this type of convergence analysis. Hashtag tag core theoretical results, the KL payoff.
Okay, so we assume this local KL condition holds for the lifted inner function f with respect to y and z. What is this bias? What does it tell us about the function we actually care about minimizing, which is x fx plus px?
This is where the KL assumption pays off, theoretically. It gives us crucial structural properties of fx. The first major result is theorem 1, local holder smoothness of f. Remember, fx is the result of that constrained, non-concave inner maximization. We wouldn't expect it to be smooth in general. Theorem 1 confirms it's differentiable under the assumptions, but more importantly, it proves its gradient satisfies that non-standard holder continuity bound we discussed earlier.
Okay. So the KL condition on the inner problem translates directly into a specific type of smoothness for the outer problem's objective function f.
Precisely. Let's look at that bound again. Equation 18. The change in the gradient, fx, is bounded by 2 terms.
Right, there's a linear term involving ilnablath x, which comes from the inherent smoothness of f itself.
And then there's the second term, LMXX. This term is the direct consequence of the KL theory.
And the exponent is explicitly related to the KL exponent.
Yes, that's the crucial link. Yef.
Yeah.
And the constant m also depends on the KL parameters c and f.
Let's trace that. If we're in the best case, the PL case, where equals 12.
Then equals 1 plus 12. 12 becomes 1.
So the second term becomes mxa1, which is just linear. The whole bound is linear. F is Lipschitz smooth.
Exactly. If the inner problem satisfies the PL condition, KL with 12, the outer objective F inherits standard Lipschitz smoothness. That's great news for algorithms.
But if F is larger, say equals over here is 34 or 0.75.
Then E offers 134, 34,
Yeah.
34, 13.
So F is only 13 Holder smooth. Its gradient is continuous, but only barely.
Right. And this has major practical consequences. What does it mean for the algorithm we'll use to minimize Fs?
Well, if F isn't Lipschitz smooth, you can't just use a standard gradient descent step size, can you? Those rely on the linear bound.
Precisely. If F is only Holder smooth with E1, the outer optimization algorithm, which turns out to be algorithm 2, the IPG method, has to be much more careful. It needs to use non-standard step sizes that diminish over iterations. And critically, it needs to restrict the domain of each step it takes. This directly explains why algorithm 2 includes that constraint, xogdxk, had to stay within a local region where the Holder property provides a useful bound. The non-standard smoothness dictates a non-standard algorithm design.
Okay, that's a huge consequence. What's the second theoretical payoff from the KL condition?
Theorem 2.
Theorem 2, local growth property of F. This one helps control the solution of the inner problem. It essentially provides an error bound in the solution space, y and z, based on the error in the function value. It says that the distance from a given point, yz, to the set of actual optimal solutions, yx, for the inner problem is bounded.
Bounded by what?
Bounded by the optimality gap, fx, fxy, raised to a power. Specifically, the exponent is 108.
Another exponent depending on d. Why is this growth property useful? It's essential for the analysis of the inner algorithm. Algorithm 1, the SCP method. That algorithm will find a point, yz, that makes the function gap small. But we need to know that if the gap is small, the point yz we found is actually close to the true optimal set yx.
Ah, it translates function value convergence into solution space convergence.
Exactly. It guarantees that achieving a small error in the inner objective means we've found a point geometrically close to the true solution set. This is crucial for ensuring the inexact solution found by algorithm 1 is good enough for algorithm 2. Tags Mangasarian-Fromovitz constraint qualification. MFCQ.
Okay, KL gives us smoothness and growth properties, but before we jump into the algorithms that use these, there's one more piece of groundwork, ensuring the constraints themselves are well behaved. Assumption 2, the Mangasarian-Fromovitz constraint qualification, or MFCQ.
Right. MFCQ is a pretty standard but absolutely vital condition in the world of constrained optimization. You see it everywhere.
What does it guarantee intuitively?
It basically prevents the feasible region from having degenerate pinch points. It requires that for any point zeta on the boundary of the feasible set, where some constraints CJY are active, there must exist a direction you can step in that moves you strictly inside the feasible region for all those active constraints.
So there's always a way to step inward from the boundary. The feasible set isn't too thin or pointy at any boundary point.
That's a good way to think about it. It ensures the geometry of the feasible set, defined by CJY, is reasonably well behaved.
Why is this specific qualification so critical here in the context of the minimax problem and the lifted structure?
Because it directly relates to the Lagrange multipliers. When you analyze optimality conditions for constrained problems, Lagrange multipliers pop up naturally. They measure the sensitivity of the objective to changes in the constraints.
Cool.
If the constraints are ill-behaved, if MFCQ fails, these Lagrange multipliers can become unbounded. They can shoot off to infinity. And that completely breaks most optimization analyses.
So MFCQ keeps the multipliers under control?
Exactly. It guarantees their existence and, crucially, their boundedness. The paper leverages this in Theorem 3. Theorem 3 applies the MFCQ assumption made on the original constraint C to the surrogate constraint used in the lifted problem. It proves something very important. Under MFCQ, there exists some positive margin. Let's call it Zia, Z0, such that for any anchor point Zia, you can always find a feasible point Y that satisfies the surrogate constraint with room to spare. That is Z, Z, Z.
So it guarantees strict feasibility, or Slater's condition, holds for the surrogate constraint system.
Precisely. And why does that matter? Because Slater's condition is key to ensuring that the Lagrange multipliers associated with the subproblems solved within algorithm 1 exist and are uniformly bounded.
Ah, okay. Lemma 1 mentions this bound, calling it A. So MFCQ is the ultimate source guaranteeing that this bound A on the multipliers exists.
You got it. So MFCQ isn't just some abstract theoretical nicety. It's the gatekeeper. It ensures the subproblems we construct in algorithm 1 are well posed, solvable, and critically, that their associated multipliers don't explode. If A were unbounded, the convergence analysis and complexity bounds for the inner algorithm would completely fall apart.
All right, the stage is set. We have the lifted problem, the KL condition providing local holder smoothness and growth, and MFCQ ensuring well-behaved constraints and bounded multipliers. Now, finally, how do we actually compute a solution?
We use a nested approach. There's an outer loop algorithm, algorithm 2, that updates the main variable x. But to do that, it needs information about the inner maximization over y. Since solving that inner problem exactly is usually impossible or too expensive, algorithm 2 calls an inner loop algorithm, algorithm 1, to find an approximate solution to the inner problem at each step.
Decoupling the inner and outer problems makes sense. Algorithm 1 needs to be accurate enough, though.
Exactly. It needs to be solved inexactly, but with a mathematically guaranteed level of precision that decreases as the outer algorithm progresses. So let's look at algorithm 1 first. Its job is to solve the inner maximization problem, max c f x y, for a fixed outer variable x. Remember, f included f matched gy, and the indicator for cy is 0. Maximizing this is equivalent to minimizing its negative. The paper defines HEs plus QZ, where GD last FXE is the potentially non-convex part, since F was an assumed concave in YZ. This is simple convex. And we have the constraint, CZ, A0.
Okay, so algorithm 1 minimizes HE subject to constraints, where H has a non-convex part G and a simple convex part Q. How does SCP handle the non-convexity of G?
SCP stands for sequential convex programming. The core idea is to iteratively approximate the difficult non-convex function G with a simpler convex model around the current iterate. Look at the subproblem in equation 27. At each inner iteration, let's say going from zk to zk plus 1, using the paper's inner loop index key, it solves. Minimize over z, zk 2 settle b, zk2 plus qz subject to the surrogate constraint, x, ct, co.
Okay, let's break that down. Ares S is a linear approximation of G around zk. L2, zk2 is a proximal term. Penalizing distance from zkz is the simple convex part we keep as is.
Right. The first two terms together form a convex quadratic upper bound or model for the change in G. Adding the simple convex function qz keeps the objective of the subproblem convex.
And the constraint is CZO. That's the lifted quadratic surrogate constraint centered at the previous point, CC.
Exactly. And here's the beauty.
Yeah.
Because kz is simple convex by assumption, and the constraint phi is defined as an intersection of Euclidean balls, based on the quadratic approximation, this entire subproblem, 27, is a convex optimization problem.
Ah, so even though the original inner problem was non-convex and possibly had nasty constraints, each step of SCP involves solving a relatively easy convex subproblem.
Precisely. That's the power of SCP. It tackles non-convexity by solving a sequence of tractable convex approximations.
What's the role of ill in that subproblem objective? It seems like a step size or Lipschitz constant.
It is. It's an estimate of the local Lipschitz constant for Yarge. Algorithm 1 uses a backtracking line search, lines 6 to 9, to find an appropriate L at each step. It starts with an estimate and increases it until a sufficient decrease condition, ln 8, is met, ensuring the step taken is productive.
Okay, so SCP iterates, solving these convex subproblems. How does it know when to stop? We need an approximate solution, but how approximate?
This is where the KL theory and the analysis connect back. The stopping criterion is given in line 10. Algorithm 1 terminates when a specific measure of non-stationarity for the lifted inner problem gets small enough. Specifically, it checks if Dister-Zasino +1 plus 1 is less than or equal to some tolerance. Here is related to the lifted objective.
So it stops when the subgradient of the lifted inner objective at the new point relative to the old anchor is small.
Essentially, yes. And crucially, that tolerance is not just some fixed small number. It's provided by the outer algorithm, algorithm 2, and it shrinks as the outer algorithm progresses, as k increases and the overall target accuracy gets smaller.
Got it. The required accuracy for the inner solve gets tighter over time. And does this process guarantee convergence?
Yes. Theorem 5 provides the convergence guarantee for algorithm 1.
It states that under the assumptions, including KL and FFCQ, the SCP method will terminate in a finite number of outer iterations, let's call it K. And importantly, this number K depends explicitly on the KL exponent clan and the required accuracy.
How does the rate depend on pay?
Lemma 9 gives the rate. If P equals 12, the PL case, the convergence is geometric or linear. That's fast. If P is in 12, 1, the convergence is sublinear with a rate like OK as PQ gets closer to 1 and the exponent gets larger, meaning slower convergence.
So the KL exponent directly dictates the speed of the inner solver. Makes sense. Can we peek under the hood of the proof slightly? Lemma 8 seems key.
Lemma 8 is indeed central to proving that finite termination. It establishes a core inequality that relates the progress made in one step, measured by Zik plus 1's K, to the non-stationarity measure used in the stopping criterion. It shows that dist Zik plus 1's K is bounded above by O's times Zik plus 1's A, where O is some constant.
Okay, so the change in position bounds the decrease in the stationarity measure. What determines this constant? Equation 33.
Depends on various things, like the smoothness constants. But most importantly, it depends on A, that uniform bound on the Lagrange multipliers we got from MFCQ via lemma 1.
Ah, so if MFCQ failed or was close to failing, A would be huge.
It would be huge. The bounded lemma 8 would be weak, and algorithm 1 might take an enormous number of steps cut to reach the required tolerance.
So the practical performance, the speed of the inner SCP solver, is fundamentally linked back to how well-behaved the original constraints are through MFCQ and the bound A.
Exactly. It all ties together.
Okay, algorithm 1 gives us an approximate inner solution, yk or zk in its own variables, satisfying the tolerance deck. Now, algorithm 2 takes this and updates the outer variable x. We're minimizing x, fx plus px. Fx is potentially non-convex and only Holder smooth. Px is simple convex. This sounds like a job for proximal gradient, but inexactly.
Exactly. It's an inexact proximal gradient IPG method. Why inexact?
Yeah.
Because we need the gradient of fx to perform the update, but we can't compute fx or its gradient exactly.
Why not?
Because fx is defined as the maximum over y of fxy. Finding that maximum exactly requires solving the inner problem perfectly, which algorithm 1 doesn't do and usually can't.
So what do we use instead of the true gradient fxk?
We use an approximation. Theorem 1 was helpful here. It showed that if yx is an exact solution to the inner problem at x, then fx is actually equal to fxyx. That is, the gradient of f with respect to x is just the partial derivative of the original f with respect to x evaluated at the optimal inner solution y.
Okay.
Since we don't have the exact yxk, but we have the approximate solution yk from algorithm 1, we use xfk, yk, as our inexact gradient for f at step k.
Makes sense. Use the gradient of f at the approximate inner solution. Now, what does the update step line 4 look like?
It's a standard proximal gradient update structure, but with the inexact gradient and a careful step size, and crucially, a constraint. x8 plus 1 argmin, xxk, ik, x, xku plus x2, xk plus px. Now, but this minimization is done only for x within a ball. BXK.
Okay, let's unpack that. The first term uses the inexact gradient. The second is the quadratic proximal term with step size 1L. The third is the simple convex function px. That looks like a standard prox gradient subproblem. But why the constraint? Why xk, bxk? Why restrict the step?
Because of the smoothness. Remember theorem 1. It only gave us local Holder smoothness for f. The approximation xs, fnxky, hey, and the Holder bound are only guaranteed to be reasonably accurate within some local neighborhood around xk.
Ah, so we have to keep the step xk plus 1 close enough to xk to stay within that region of validity?
Exactly. The radius r of this ball is chosen carefully based on the analysis. It's given as r equals JLA 4LF, where JLE is our final target accuracy for the overall problem, and JL are the locality parameters from the KL level set definition, LX.
So the allowed step radius depends on the final accuracy and the KL locality parameters.
Wow. It's a direct consequence of relying on a local non-standard smoothness property.
What about the step size parameter ELK? Is it constant?
No, it's also non-standard and adaptive.
Yeah.
It has to account for two things: the inexactness of the gradient and the Holder smoothness, if L1. ELK is determined by the base smoothness LF, but it's increased by a penalty term that involves M, the Holder constant from theorem 1, and the Holder exponent DL1. It also includes a term Kac that decays with K, related to controlling the error from the inexact gradient.
So the effective step size, 1 ELK, is potentially quite small and changes at each iteration, directly reflecting the underlying Holder smoothness and the inner approximation quality.
Precisely. It's a carefully engineered step size rule required by the theory. Using a standard fixed step size would likely cause the algorithm to diverge.
And finally, line 5 connects back to algorithm 1. It calls the inner SCP solver with that decreasing tolerance.
Right. EC is chosen to shrink appropriately with K and A to ensure that the error introduced by using the inexact gradient or Check-yes fxkyk is controlled well enough for the outer IPG iteration to converge. The accuracy of the inner solve needs to keep pace with the progress of the outer solve.
Okay, we have the theory. Based on KL, we have the two algorithms, inner SCP, outer IPG, designed around that theory. Now for the payoff. How fast does this whole thing actually converge? What are the complexity guarantees?
This is arguably the main contribution of the paper, providing explicit complexity bounds for this difficult class of problems. But first, we need a precise definition of what counts as a solution. We're not usually going to find an exact stationary point.
Right. We need an approximate stationarity concept.
Definition 1 introduces the stationary point. This definition is slightly subtle because of the local nature of everything. We don't require the final point x itself to satisfy distance core. Instead, we require that the final point x be close, within distance r, to some point x that does satisfy the condition distance core. Okay. So we just need to land near the set of true stationary points, which they call x. The radius r is the same one used in the algorithm's step constraint.
Exactly. It accounts for the fact that our analysis and algorithm steps are inherently local. #hag the iteration complexity, theorem 6.
With that definition, theorem 6 gives the iteration complexity. This is co, the number of outer loop iterations algorithm 2 needs to find an r stationary point.
Yes. And the bound looks pretty intimidating, but let's focus on the dependence on the target accuracy, the ignoring logarithmic factors, the tilde and O. The complexity is proportional to passive raised to the power of minus max.
Okay.
That exponent is key. It's determined by the maximum of two terms, both coming directly from the KL analysis.
Right. Let's analyze that max term. It represents a competition between two factors governing the difficulty.
The first term is 1 hell. That looks familiar.
It comes directly from the KL exponent. It reflects the inherent geometric difficulty of the function landscape near the solution, as captured by KL.
What does it mean if this term dominates the max?
If 1 has a larger than fel, then the complexity is primarily limited by the function's geometry itself. Let's consider the best case. L equals 12, PL condition.
Then 1 was for his actual 2, excess 1 to 12 equals 2.
So the exponent contribution is -2. That's good polynomial dependence on L.
But if L is close to 1, say PL 0.9,
then 1 equals 10.1 equals 10. The exponent contribution is -10.
and an L equals 119.
Then 1 which equals 100. The exponent contribution is -100. You see the pattern. As A approaches 1, weaker KL condition, flatter landscape, the denominator 1 goes to 0 and this exponent explodes. The complexity gets exponentially worse.
So this term represents the penalty for the function being inherently difficult in the KL sense. What about the second term in the max?
This term relates to the locality of the KL assumption. Remember, SUF controls how quickly the level set LX shrinks as we approach the solution.
Right. LX was defined by gap Lesta.
It's as large, it means the KL condition only holds in a very, very tiny region once X gets close to stationary. The assumption becomes highly localized.
So SUF dominates the max.
Then the complexity is limited not so much by the function's intrinsic geometry, but by how restrictive our assumption about where the KL condition holds becomes near the solution. A large SUF effectively forces the algorithm to take smaller, more careful steps, increasing the iteration count.
So the overall iteration complexity is determined by whichever is worse. The function's inherent KL geometry or the rate at which the required local region shrinks.
That's a perfect summary of the iteration complexity exponent. #tag first order Oracle complexity theorem 7.
Okay, K is the number of outer steps. But each outer step involves running the inner SCP algorithm, algorithm 1, which itself takes multiple steps and gradient calculations. The real measure of computational effort is the total number of gradient calls, right?
Absolutely. That's the first order Oracle complexity denoted N in theorem 7. This measures the total number of times we need to evaluate F, or technically Jackson F. Getting N involves multiplying the outer iteration complexity comb by the complexity of the inner algorithm, algorithm 1 per outer step. The formula looks even more daunting.
Let's try to simplify again by focusing on the dependence on EC and N and the KL exponent. Can we analyze the best and worst cases for N?
We can. Let's start with the best case again.
Yeah.
Case 1, EC 12, PL case. But
Yeah.
EC there is 12, the analysis simplifies considerably. The total oracle complexity n becomes O actix 2 max 1.
Okay, unpack that. If small, say a c at 1, which seems reasonable, controls the shrinking rate exponent, then max 1 is just 1.
Right. In that common scenario, the complexity is O.
Oh, that's fantastic. That's the same rate as standard gradient descent for smooth non-convex optimization. It means that if the inner problem satisfies the PL condition, KL with M1, this whole complex nested algorithm for the constrained non-convex, non-concave problem achieves the optimal complexity rate known for much simpler problems, up to log factors.
Exactly. It shows the framework is highly efficient in the best-case scenario allowed by the theory. The locality parameter introduces a potential penalty if things hone, making the exponent -2 instead of 9 of 2, but the dependence on events remains polynomial and relatively good.
Okay, that's the good news. Now for the general, potentially harder case, case 2, made 12.
1. This is where the complexity starts to look painful. The exponent on hum becomes much worse. It's a product of terms related to the inner complexity and the outer complexity, both depending heavily on wax. The paper gives the explicit formula, which is quite dense. Let's focus on that something multiplier in the exponent, which comes from the inner loop cost. It's given as 2 thim plus 1 hum.
Okay, so the full exponent is 2 plus 1, 1 max, 1 lengthy.
Yikes, yeah, it's not pretty. Let's analyze the numerator. 2 plus 1. When in Theo, it's 214, 212 plus 1 plus 1 plus 1 gives 12. When approaches 1, let's say Yalobio, where or is small and positive, then 2, 1 will be 2, 1, and 2, 1 to 2 plus 2 plus 1 plus 2 plus 2 plus 1 approaches 1. So it approaches 1. The term 1, however, in the denominator still goes to 0. So that first fraction still blows up as it approaches 1.
So the total exponent gets really bad really fast as e increases towards 1. Can we use that concrete example from before? Compare a component for couple 12 with the case A0.9?
Let's try. Assume C is small, so max is dominated by 1, 1 dot. If U12 exponent is minus 2, complexity CO. If it assumes 8.9, then 1, but the multiplier is 2.81 plus 1 plus 1 per 1.8 plus 1.8 plus 1.1 plus 1.1 plus 1.1 plus 0.1 equals 0.1 equals 8.2. So the total exponent is roughly and is 8.210 gives rid to A2. The complexity is O.
From AWA to AOA, that's astronomical.
It shows the extreme sensitivity to the KL exponent. Reducing the error by a factor of 10 might cost 10 mana equals 100 times more effort in the TO12 case, but 10 arrow times more effort in the HALE.9 case.
That is an incredibly sharp dependency. It really hammers home that if the underlying mathematical geometry forces to be close to 1, these first-order methods, even sophisticated ones like this, become computationally infeasible very, very quickly for high accuracy.
Absolutely. The complexity analysis doesn't just say it converges. It provides a precise mathematical explanation for why certain problems are computationally hard, linking the geometric property TLA directly to the total number of required gradient evaluations. It's a quantitative measure of difficulty. Hashtag tag numerical illustration, section 5.
Okay, that's some heavy theory and complexity. To make this more concrete, the authors included a numerical example, right? Section 5.
Yes. They applied their framework to a specific custom-designed test problem given in equation 43. It's not a standard benchmark. It's constructed to fit their problem structure. 1. It involves quadratic terms, Hadamard products, element-wise multiplication, and importantly, exponential constraints on the inner variable y. It's definitely non-convex, non-concave, and constrained.
So a complex setup designed to test the machinery. What parameters did they assume for the KL condition in their test?
They actually set the parameters to the most favorable case allowed by their theory. They assumed the optimal PL condition holds, setting U equals 0.5. And they chose a relatively small locality parameter, 0.1.
So they tested the algorithm under the best-case structural assumptions, where we expect the best complexity.
Exactly. It's essentially a test of whether the algorithm performs well when the theory predicts it should.
They ran algorithm 2, the outer IPG loop, for a fixed number of iterations, 2,500, across various problem dimensions, n1 for x, n2 for y. The results are in table 1. What were the key takeaways?
2 main things stand out from their table. First, the algorithm consistently and significantly reduced the objective function value x from its starting point. It went from positive values down to large negative values, clearly demonstrating progress towards a minimum.
So it works in practice, at least in this ideal setting. What was the second key takeaway?
The second point is maybe more subtle, but validates the theory. They compared the final objective value calculated exactly at the endpoint, x,
which requires solving the inner problem accurately just once at the end, with the approximate objective value computed using the final inexact inner solution you found by the algorithm during its run.
And how did they compare?
They were extremely close. The difference between the true x and the approximate x was very small across all dimensions tested.
Why is that comparison so important?
It validates the entire inexactness approach driven by the KL theory. It shows that the sophisticated stopping criterion used for the inner solver, algorithm 1, which only demanded an approximate solution, yt outside the tolerance spec at each outer step, was actually sufficient. The algorithm didn't need to waste huge amounts of effort finding near-perfect inner solutions at every single outer step. It only needed solutions that were good enough according to the KL-based tolerance, and the final outer solution x still landed in a place where the true objective value was low and very close to the value estimated using the last inexact inner solution.
So it confirms that the whole theoretical machinery translating KL into stopping rules and step sizes actually works efficiently in practice. The inexactness was managed correctly.
Precisely. It demonstrates the practical efficacy and efficiency of combining SCP and IPG guided by these carefully derived KL-based criteria, at least under the favorable assumption. #tag@row.
All right, let's try to wrap this up and synthesize this deep dive. What's the big picture here? The major contribution seems to be establishing, really for the first time, a comprehensive algorithmic framework.
Yeah, one that comes with concrete performance guarantees.
For solving these notoriously difficult, constrained, non-convex, non-concave minimax problems. And the framework combines several sophisticated ideas. The lifted problem structure, the local KL condition, sequential convex programming for the inner loop, and inexact proximal gradient for the outer loop.
Absolutely. And the linchpin holding it all together, the theoretical engine, is that local KL condition, assumption 1. It had to be applied to the carefully constructed lifted problem F by rigorously working through the consequences of that assumption, establishing the connection between the optimality gap and the subgradient slope, deriving the resulting non-standard local Holder smoothness, theorem 1, and the local growth property, theorem 2. The authors built the necessary mathematical machinery.
Machinery that doesn't just prove convergence, but allows them to quantify the convergence rate, to precisely characterize the computational effort required, showing how it's dictated primarily by those two key parameters, A and suc, derived from the KL condition itself.
Exactly. It's a really impressive example of how you engineer algorithms specifically tailored to the potentially poor geometric properties of the functions you're dealing with. They found a way to translate this abstract mathematical property, the KL inequality, into very concrete practical things like step size rules and stopping tolerances for the inner solver, all designed to work even for this challenging class of problems.
It really bridges the gap between abstract, non-smooth analysis and practical algorithm design with guarantees.
Indeed. And this leads us naturally to a final provocative thought for you, the listener. We saw how incredibly sharp the dependence of the complexity is on that KL exponent 3. It blows up as they approaches 1. Now, these constrained minimax problems are fundamental to really important cutting-edge applications. Think about training constrained generative adversarial networks, GNNs, for realistic data generation with specific properties, or calculating complex economic equilibria with constraints or robust control systems.
Right, problems where solutions are critical but hard to find.
So here's the thought. Given this sensitivity, what if we could develop new techniques? Maybe advanced smoothing methods applied to the functions, or clever regularization strategies added to the problem formulation that could mathematically force the effective KL exponent to stay closer to the ideal value of 12, even for inherently complex real-world functions.
If we could somehow pre-process or reformulate the problem to ensure it satisfies something closer to the PL condition,
How drastically could we improve the actual training efficiency, the speed, and the reliability of finding good solutions for these foundational machine learning models and optimization problems in practice? That's where the frontier lies, manipulating the mathematical structure, like to unlock major real-world computational breakthroughs.